Il faut qu'ils viennent et après, bon, ils peuvent repartir pour l'enregistrement.
No, sorry. That's it.
Ok, à tout de suite.
Good morning, ladies and gentlemen. The opening ceremony of the international conference will begin with a welcome address by the rector of the National and Capodistrian University of Athens, Professor Meletios Athanasios Dimopoulos.
Dear Rector Boudouvis, dear professors, dear members of the organizing committee, esteemed guests, dear colleagues, dear participants of the NASCA 23 conference, it is a pleasure to extend a warm welcome to all of you attending the International Conference on Numerical Analysis and Scientific Computation with Applications, NASCA 23, organized by the Faculty of Mathematics of the National Capodistrian University of Athens in collaboration with the Université du Littoral Côte d'Opaleษ์, Ulco, France. Our university was founded in 1837, and it was the first university in the newly established modern Greek state, but also in the Balkan area and Eastern Mediterranean area. Its role has been decisive for education and promotion of cultural life in the country and beyond. It emerged in the midst of socio-economic changes from the very start of his establishment, and it keeps surfacing for its high standard human resources and its deep-rooted tradition. Our university is also a research-intensive university, and internalization is one of the cornerstone goals of our 10-year strategic plan. We actively promote worldwide networking at an institutional level. Our faculty and researchers continuously challenge the boundaries of knowledge, providing the highest learning opportunities for our students. Our university collaborates with universities, research centers, university networks, as well as international educational organizations in order to develop common practices, strengthen research collaborations, and encourage mobility of students, researchers, and academics. As a rector of this university, I fully support initiatives regarding not only our university's extroversion, but also the essential diffusion of academic knowledge and research as a key to innovation. I strongly believe that participation in conferences broadens our mind and is a major way to achieve all the above. Like the decimals of the number p, the experience one can have in life are infinitive. Your participation in NASCA 23 will strengthen your international academic collaboration and lead to new ones, will boost your scientific research and offer you the unique experience of being in Athens in July and also feel the wonderful summertime atmosphere. I wish to congratulate you for your participation, as well as the organizing committee and all those who worked for a successful and fruitful conference, and especially the president of Ulco, Professor Hassan Sadok, and also from the conference organizers, Professor Marilena Mitrouli and Professor Khalid Jiblu. Once again, welcome to NASCA 23, and I hope that you will have a fruitful and enjoyable time in our city. Thank you.
Address by the Rector of the National Technical University of Athens, Professor Andreas Boudouvis.
Good morning, dear Rector of the National Capodistrian University of Athens, a comrade in rectorial endeavors in the Greek academic system, Thanos Dimopoulos, dear colleagues from Greece and abroad participating in the Numerical Analysis and Scientific Computing with Applications 2023. Ladies and gentlemen, it's my pleasure to be here, and I thank the organizers, especially Professor Marilena Mitrouli and Professor Khalid Zblou for the co-organizing institution Université de Littoral Côte, Opaleษ์for the invitation to this conference. Representing as rector the National Technical University of Athens, NTUA, I take this opportunity to mention that numerical analysis and especially scientific computing have center stage in undergraduate and postgraduate curricula at NTUA, and more so in the diverse research activities at NTUA. Let me briefly introduce my university. NTUA is, together with the University of Athens, the oldest university in Greece, and it has contributed unceasingly to the country's scientific, technical, and economic development since its foundation in 1837. It is also the leading technical university in Greece, the alma mater of many scientists in Greece and many distinguished academics in the diaspora, especially in North America and Europe. NTUA, with 15,000 undergraduate students and 400 faculty members, comprises 9 academic schools: chemical engineering, electrical and computer engineering, mechanical engineering, civil engineering, architecture, rural surveying and geoinformatics engineering, mining and metallurgical engineering, naval architecture and marine engineering, and the School of Applied Mathematical and Physical Sciences. NTUA excels in research performance. Together with its own Institute of Communication and Computer Systems, is the national champion in competitive European research funding, and so far ranks number 15 at the Horizon Europe program, which spans the funding period 2021-2027. As I mentioned, NTUA values applied mathematics, and actually it is in the very advantageous position to attract the best graduates from secondary education in mathematics and physics. The motto of NTUA is based to the three-legged stool of scientific progress pertaining to engineering science: theory, experiment, computations. Having said that, let me make a personal note. The motto I just mentioned was strongly founded in me during my time as a PhD candidate at the University of Minnesota, the Department of Chemical Engineering and Material Sciences, in the 80s and later in the 90s as a visiting scientist. It was at that time that I was exposed, together with the whole research group of my advisor at that time, to the legendary works of Youssef Saad, later to join the University of Minnesota. And I'm so glad that he is here in this conference. Iterative methods for solving large and sparse linear systems and eigenvalue problems was at those times at the center of attention and practical use for researchers in fluid mechanics and practitioners of the discretization methods like the finite elements. I am indebted to Professor Saad for what he has offered to the computational engineering science community. Let me close by reconnecting with the motto, theory, experiment, computations. It's not only the first part that is theory, but especially the third part, computations, that are indispensable, along with the advent of high-performance computers, in order to interrogate effectively and efficiently the partial differential equations for the conservation of mass, momentum, and energy, the basis in engineering theoretical modeling from first principles. They were desperately needed back in the 90s. They are still needed for the same purpose, while striving to survive in competitive coexistence with machine learning and big data in the artificial intelligence era. May I also say regarding the latter that experiments are providing data which are needed in huge quantities for the training and validation of the neural networks. And if they are not huge enough, then simulations are the only substitutes. With that, I wish you a fruitful conference, have a pleasant stay in the city of Athens, and relaxing summer vacations. I will be around again tomorrow at 3 p.m. with my plenary talk. Thank you.
Address by the President of the Université du Littoral Côte d'Opaleษ์, Professor Hassan Sadok.
Dear Rector of the National and Capodistran University of Athens, Director of the National Technical University of Athens, dear Professor Ahmed Ratnani, representing Université Polytechnique Mohammed VI of Morocco, dear colleagues and friends. Before we start the exciting topics and discussion that lie ahead, I would like to express my sincere gratitude to all the organizers, sponsors, and people who have worked hardly to make this conference a reality. It's thanks to their dedication and the passion for scientific progress that we gathered here today. The aim of NASCA 2023 is to foster collaboration and knowledge exchange between researchers working in various fields of numerical analysis, scientific computing, and applications. We have an impressive list of speakers and many symposia, offering a wide range of perspective and expertise. I would like to thank all speakers who have graciously agreed to share their knowledge and idea with us. Of course, I am very happy that the research paper dedicated issue of this international conference will be published in Applied Numerical Mathematics and Computer and Mathematics with Application. Finally, I would like to express my deep gratitude to Professor Marilina Mitroli and Professor Khalid Bilou, who played a key role in the organization of this event. Their tireless effort and unwavering commitment to excellence ensured that the conference ran smoothly. I am convinced that NASCA 2023 will serve as a catalyst for new discovery, collaboration, and breakthrough in numerical analysis, scientific computing, and applications. Let us take this opportunity to engage in fruitful discussion, foster new connection, and contribute to the advancement of our collective knowledge. Thank you all for joining us today, and I wish you a productive and enjoyable conference.
Address on behalf of the conference organizer by Université du Littoral Côte d'Opale়.
Okay, thank you. Morning, and welcome to this nice conference. I think Hassan Sadok introduced the conference and talked about this organization. So I would like just to tell you that this conference is the fourth one, because in '92, the first one was in Morocco, in Agadir, in 2009. The second one was in Calais, in France, in Littoral, in 2013. The third one, the very nice one, was in Kalamata, near the sea. And this one, next one, we hope in Greece also, maybe in Kalamata, we'll say. And I would like to thank all the invited speakers, Youssef Saad, Marcos Raidan, Froilando Pico, Mr. Boudovis, Mr. Hassan Sadok, Mr. Ahmed Ratnani, and also Michele Benzi, who will give a talk on Thursday, but via Zoom. He couldn't be present. And unfortunately, Lothar Reichel normally should be here, but some problems, and he told me to say hello to all the participants. So I would like also to thank quickly the organizing committee, the international, and especially the local organizing committee. I'd like to thank especially some students who did a hard job to make this conference a good conference. And I would like to thank the sponsors. We have many sponsors: the University of Athens, the two universities in Athens, the Littoral, University in Morocco, my department, and special thanks also to Mr. Petridi, who is now, I think, 101 old. And he is a famous mathematician, and he participated to this conference. So I would like to thank him. And last thing, I would like to mention that we have two special issues for this conference. The first one, the first journal is, both of them are very good journals. The first one is Applied Numerical Mathematics, and the second one is Computation and Mathematics with Applications. Okay. I'll give more information by email at the end of the conference, but normally the deadline should be around the beginning of October. So, but you will have more information about that. So, welcome to this conference, and enjoy, especially Athens. Thank you very much.
Address by the Dean of the School of Science of the National and Capodistrian University of Athens, Professor Ioannis Emanuil.
Good morning, everybody. First of all, I would like to apologize for being late, but I had another engagement in a university campus in Kessariani, another meeting on geoscience and geoenvironment. Honorable rectors of the National and Capodistrian University of Athens, of the University of Littoral Côte d'Opaleษ์, dear members of the organizing and the scientific committees, dear colleagues, dear students, I would also like to welcome you in this impressive hall of the National and Capodistrian University of Athens on the occasion of the Conference on Numerical Analysis and Scientific Computation with Applications, NASCA 23. For our guests from abroad, I would like to point out that this hall has witnessed some very important moments in the history of the modern Hellenic state during the past 200 years or so. In fact, the National Capodistrian University of Athens was founded only a few years after the very formation of the modern Greek state. The success of the previous conferences of the series has already placed some very high standards on the present conference. I was impressed going through the names in the list of speakers and participants. The titles of the talks guarantee that the conference will be very interesting and will certainly live up to these expectations. I am sure that all participants will benefit by attending the lectures, as well as from participating in the informal discussions that will take place during the breaks of the meeting. Mathematics stands at the very center of modern science and fruitfully interacts with many other disciplines, such as physics, biology, and engineering. The interaction goes both ways. On one hand, mathematics provides other sciences with rigorous methods and powerful techniques, which are very often adequate to solve the problems that are encountered therein. On the other hand, problems that appear in science provide a challenge for mathematicians to construct a theoretical model that describes the physical phenomenon under investigation and then develop the necessary tools for its study. The complexity of the problems that are often encountered in science makes the search for an exact solution very difficult. In practice, what one needs is a fast and inexpensive computational method that offers approximate solutions with a prescribed degree of accuracy. This illustrates the importance of the topics of the conference: numerical analysis and scientific computing, with an emphasis on applications. The hosting of the conference by the Department of Mathematics represents an extroversion activity organized by members of the department that expresses in a very eloquent manner its international orientation. It goes along with the corresponding extroversion and internationalization policy of our university. The exchange of ideas and the dissemination of knowledge is very important for the progress of science. Conferences such as the one that starts today aim, among other things, to promote collaboration between scientists, with a special focus to the new generation of researchers and students who are expected to gain valuable experience by participating in the conference and discussing their ideas with more senior and established scientists. I would like to conclude this short address by congratulating the organizers for their efforts. I heartily wish every success to the conference. I am sure that there will be many interesting lectures and productive discussions. Dear guests, I hope that you will enjoy the hospitality of the Department of Mathematics and benefit from attending the conference. Stay healthy and enjoy the talks, as well as your stay in Athens, of course, during these warm days of July. Thank you very much.
Address on behalf of the conference organizers by Professor Marilena Mitrouli, National and Capodistria University of Athens.
So, hello everyone. I think that maybe it's better I can avoid speaking on the microphone. I think I can do it like this better. I am very happy that the fourth NASCA conference takes place in Athens, and specifically in this historical building, which is actually a jewel for our country. And this is really a great pleasure for me. As organizing committee, we worked hard in order to provide to the participants two important things. First of all, unique collaborations of high scientific quality, and this is guaranteed by our invited speakers, by our participants that we have the honor to come here and give with their presence the participation to the conference. And on the second hand, we want to give some nice social events which will be related with our university and its history. And I will emphasize 3 points. First of all, the conference conference material. As you can see, inside the bag, we have a very nice book of abstracts. The cover of the book actually is the entrance of our university, the so-called Opaleษ์, and it is specially made for NASCA participants. In the back, there is the history also of the construction of this called Opaleษ์. Also, the notebook of the conference contains in the cover the symbol of our university, the goddess Athena, which according to the ancient Greek mythology was the goddess of wisdom and reading, so suits very well with university and with reading and collaborative work. The second thing, the conference dinner, which will take place tomorrow evening, will be in Plaka, in the first historical building that University of Athens operated in 1837. This building is just underneath Acropolis, and for the time being when it started its operation, it had only 30 students. So you will see also this building tomorrow evening. And the third part, that is the conference excursion, will be in Sunio in order to admire the Temple of Poseidon, which, according again to Greek mythology, quarreled with goddess Athena, who will give the name to the city of Athens. And of course, Athena won the whole competition. The town is called Athena, and as a reward to Poseidon, they made this temple in Sunio, just above the Aegean Sea, which is really magnificent, and I think it's very nice also to visit and admire it. So, once more, thank you very much for your participation, and I hope to enjoy the conference and your stay in Athens. And also, before closing, I will ask, we have also, as representative of Open University, Professor Maria Hatzinikolaou, to give us a brief greeting. So, welcome from me, and hope to enjoy the conference.
Just impromptu, I wasn't prepared to address the conference, so on behalf of Hellenic Open University, just very newly university, it's only 30 years old, dear honorable representatives of the universities, dear invited speakers, dear colleagues, dear guests, I'm very pleased to welcome you in this conference, and I hope seeing very deeply the program, I'm sure that it will be a very interesting and tempting and giving food for thought and initiate discussions and collaborations among all of us towards in the disciplinary communication of science and its applications. So thank you very much. I'm very pleased and thank the organizers for this invitation. And I hope we have all fruitful discussions and conference. Thank you very much.
A short video on the history of the National and Capodistria University of Athens will follow.
'37 is the year of higher education. The opening occurs on May 3rd in the presence of the king, authorities and residents of the capital who embraced the new establishment from the very beginning. The university is housed at the residence of architect and city planner Stamatis Kleanthis. It is one of the very few large buildings in Athens at the time.
The Ottonian University starts with 4 schools: law, theology, medicine, and philosophy. In keeping with the tradition of German universities, the School of Philosophy contains the departments of philology and physics and mathematics.
students are only male. In the first years, most students are expatriates from the Ottoman Empire. In the first year, classes are attended by 52 students and many auditors.
On July 2, 1839, King Otto lays the cornerstone for the university's central building.
The main wing of the building, known as Propylaea, is completed in 1841 and classes are transferred there.
Only men are allowed to study up until 1890. Very early on, they become extremely active participants in the university.
They make their presence strongly felt in the streets of Athens, pursuing demands related to the university and other topics.
In 1862, Otto's expulsion heightened students' stature as a driving force in the struggle against oppression.
In October 1862, the provisional government changes the university's name from Ottonian to National. A new era begins. The institution will gain even greater prestige.
Symbols of the old regime are eliminated along with the old name. Royal decorations on the university seal are replaced by the image of an owl, a symbol of wisdom. In 1887, in celebration of 50 years of operation, the university acquires its banner.
At the end of the 19th century, the university undergoes several major changes. The first female student, Ioanna Stefanopouli, registers at the School of Philosophy in 1890. Positivism makes its presence strongly felt, reflected in the founding of museums and the creation of dozens of laboratories and tutorial facilities. Among them is the new chemistry laboratory, one of the best of its time. The Venizelos era begins in 1911, when the government of the Cretan politician votes for the first definitive university regulation.
A temporary one had been in operation previously for 80 years.
The university is expanding, not only in terms of staff, but also infrastructure. Schools acquire new buildings, such as the Theoretical Disciplines Building and the School of Medicine. The expanding student population makes the issue of their representation ever more critical. In 1911, the rector gives permission for the formation of student unions and societies. It marks the beginning of the student union movement and politicized trade unions.
At the same time, left-wing ideologies begin making their way onto campus. The student movement becomes much more politically aware and simultaneously more critical of the university itself. The map of higher education in the country changes drastically with the founding of the University of Thessaloniki in 1926. That's followed by a series of other new schools, founded by Venizelos governments in an attempt to connect education with production. From the 1990s onwards, with populations of both students and staff growing steadily, the university's implementation of postgraduate studies and European research programs contributes significantly to advancing research infrastructure and related activities.
In these 180 years, millions of people have walked the hallways of NKUA, students of both genders, educators and administrators. The majority of those who appeared on the country's socio-political stage, at least until the interwar period, came from the National and Kapodistrian University of Athens.
Presidents of the Republic, prime ministers, cabinet ministers, and more have served as members of its educational staff. Globally prominent figures in science and culture have studied at NKUA. Since its founding, NKUA has, to a great extent, served as the backbone of the country's scientific, social, and cultural life. Today, it consists of 8 schools and 33 departments. Its educational and administrative staff number more than 3,000 people, and it serves more than 65,000 students.
Its historic tradition, the scientific reputation of its educators, the contribution of its researchers and administrators, the vitality and potential of its student body, these attributes are the compass that will allow the university to continue navigating successfully into the 21st century.
Okay, I think we should start. Our first prayer speaker.
Thank you for the nice introduction. Hello, everyone. So I'd like to thank the organizers for putting together this nice meeting. This is a very nice setting, I have to say. Also, I have to, this is very special to me. Look at the, when you look at the symbols, the writing in here, it looks like mathematics, right? Because we use these symbols when we do mathematics, and we have to be reminded that we're not too far from the birth of mathematics, right? Very special. So, I would like to just say the collaborators on this work. This is going to be a talk on nonlinear accelerators, and it will be partly a review, partly on this work on nonlinear truncated generalized conjugate residual approach. So there are two papers that I will mention here that are related. The first one is actually now in archive, and the second one is in a paper that has appeared a few years back. So let's just start with an introduction. When you look at accelerators for linear systems, you think of conjugate gradient, conjugate residual, GCR, orthomin, etc. Those are Krylov type methods. But when you deal with nonlinear systems, the picture is much more complex. Linear accelerators involve, you can have three different pictures, actually, three different views of the whole thing. You can have linear accelerators that are invoked when you solve Jacobian systems iteratively in Newton, and then you get what is called inexactness methods. You have quasi-Newton type methods, things that essentially approximate the Jacobian as you go. And then you have Anderson accelerators, things like Poulet mixing, and all those are really geared towards accelerating iterations. This talk will take the viewpoint of extending non-symmetric Krylov methods, linear ones, to nonlinear settings. There are many different approaches, and I want to convince you that there's a lot to be done here, and the picture is very complex. There's a lot of nuances when you compare this to what happens in the linear case. Okay? So one specific goal is to unravel algorithms with short-term recurrences. I will explain that. So let's go back to extrapolation. People who worked on acceleration techniques and extrapolation techniques, and there are quite a few. Okay, this is better? Okay. People who worked on extrapolation, and there are quite a few in this room, know that when you have a sequence, whether it's vectors or scalars, you can get better sequence by just combining those iterates, those terms of the sequence. And this is what is the formula you see on the top here. This is how you can point to the okay, it's okay. So the history actually of this thing is quite long. We have Richardson acceleration techniques that appeared in the early 90s, in the 1900s, and then you have Aitken, Romberg, who used these acceleration techniques for integration. Then appeared a paper by Shanks in 1955, which generalized Aitken's method, and Wynne found a very elegant way of implementing those techniques. And this set up really a flurry of activity in the late 60s and early 70s. It was really a very nice kind of discovery that was followed by a lot of people, and you can see some names of some people here who worked in this area. At the same time in physics, people worked on approaches like Anderson mixing and so on. And I just want to mention that earlier we talked about, there was a talk about the times a few years back in chemistry, in chemical engineering rather, in Minnesota. Those kind of things were actually the types of methods that were used at the time, acceleration type techniques and so on for physics. The viewpoint is closer, in this case, is closer to what we call now quasi-Newton than to extrapolation. And then we have, of course, linear algebra in numerical algebra, we have all these methods to accelerate sequences starting from Chebyshev to things like MPE, etc. They're all based on similar things, essentially take the combination of the previous iterates and then try to get a better iterate from those. So here's a slightly more detailed picture on acceleration. So I'm going to distinguish between extrapolation and acceleration. Very often, what you have is, here we go. You have a sequence like this one, which is fixed point iteration, and you would like to accelerate the sequence simply. So you have access to the function g. So essentially, what you do is, in a way, trying to solve the system, x minus g of x is equal to 0, by creating a sequence that invokes the function g and the previous iterates. This is one viewpoint. So we're trying to solve, essentially, to find the 0 of this function. But the only restriction when we look at these approaches is that we only, the iterates would generate only involve this function g and the previous iterates. So you cannot access to other complicated things. That is a little bit more restrictive than extrapolation, where you only access the iterates. So there's a little distinction here. Okay. So here's a picture of the 3 types of methods. You have extrapolation, which essentially builds a new sequence from another sequence, which hopefully will converge faster. Then you have quasi-Newton type methods, where you're essentially solving f of x is equal to 0, where f is the function that I had earlier here. Okay? And then you have these acceleration type techniques like Anderson, et cetera, Opaleษ์, et cetera, where you're trying to figure out a way of minimizing this function based on these different differences. So I'm going to spend a little bit more time as a background on inexact Newton, quasi-Newton, and Krylov-Newton methods. So here is Newton approach. You can see that. Okay, I'm sorry. So you can see that you're solving a system here with a Jacobian at xj, and you set the new iterate this way. This is a very basic method, okay? And often what people do is, of course, they don't solve the system exactly. They solve it with some iterative method, and then you call this approach an inexact Newton method. And there's a lot of work that has been done in here to figure out ways of ensuring convergence, for example. For how you solve the system approximately, what do you require to get convergence? Then another set of approach, which is completely different, is to use quasi-Newton type method. In this case, you solve the system by approximating the Jacobian or its inverse with gradually by using the previous iterates. Okay? So this is also a very big class of methods. It has generated a lot of work. And then Newton-Krylov methods are essentially inexact Newton type methods where the solve for the system uses a Krylov method. And you have to remember that you don't need really the Jacobian J explicitly, Jacobian of F explicitly. When you apply it, you use this formula, differentiation formula. So that requires one function evaluation. Okay. The important consideration here, which is actually a drawback for this type of inexact Newton methods, is you need to compute something like this, as you can see it here, for small epsilon and the vector v. For xj here is fixed, and you have a v that comes in, and you need to compute this. So this is a contrast. We're using just the xj's and fj's as is done in these acceleration techniques. You have previous iterates, you have the function evaluations for those, and then from those you get some approximation to the Jacobian, or you get, so that is a big distinction. I think this is a drawback of these inexact Newton type approaches. So Here is the inexact Newton approach, okay, where you solve the system approximately. So this is, I'm repeating here. I'm going to just now look at specifically when you use Krylov methods. So if you use Krylov methods, you use essentially an approximation will be generated from the subspace. So the approximation delta that you use here, this delta, is taken from this subspace. Okay? J is the Jacobian at the current iterate. So then it is essentially of this form. Delta J is of this form. So it's a combination of the VI, some VL as a basis of the Krylov subspace. So you're taking a combination of these columns, and you can think of delta J as being in this form. So actually, delta J is exactly this. In the case, for example, when you use FOM, okay, the full orthogonalization method. So this is interesting because you're looking at delta J that's given by a combination of vectors. So you can think of this matrix that you see here that's applied to minus f of xj as an approximation to the inverse of the Jacobian, right? Because this is what we want. We want to get the approximation to the inverse of the Jacobian, and this is the approximation that's implied by this approach. So that's what you see here. This is the approximation to the Jacobian that is used to get the iterate. For GMRS, you have something like this. It's just a different formulation, but uses the same V here. So this is interesting to see that you can formulate these in a way as you're always getting a low-rank approximation to the Jacobian in these methods as well. In quasi-Newton method, we don't do that, but you essentially use the previous directions to generate the Jacobian, an approximate to the Jacobian. Let me see if I can find that here. Oh, here we go. Okay, so then you take all these differences, the xj's and fj's. By the way, the xj's are the previous iterates, and the fj's are the values, the evaluations of f at those xj's. That's what you see here. And then you can impose these two conditions, the second condition and this no change condition, and it's a very simple algebraic argument of dimension shows you that there is one unique J that satisfies these two, and that what Broyden did, and they found that the formula to get the approximate Jacobian is this one here. So you can see that you're updating the new Jacobian for the previous one by adding a rank 1 approximation. So type 2 Broyden approach, the type 2 Broyden approach does the same thing, but approximates the inverse instead of the Jacobian itself. And there are some considerations that show that maybe this is not as good. I mean, it's all mixed, not really clear. This is quite efficient in some situations. Okay, so there's two approaches are, in both cases, you're looking at an approximate inverse of a Jacobian anyway. So, but this difference between the Newton, the inexact Newton is here we're really getting an approximate Jacobian by one rank at a time. So you're updating the Jacobian by one rank at a time. And you don't waste any extra function evaluations. Whatever has been evaluated is used efficiently to compute, to update this new approximation. So there's a lot of work on those, and there are quite a few courses available that implement those. Now let's look at Anderson acceleration. So Anderson acceleration is geared towards accelerating a fixed point iteration. So remember, in my notation, we're looking at G is the function that is used for the fixed point iteration. Xk plus 1 is G of Xk. So I'm trying to find a zero of this function f. So think of beta as being equal to 1 only. So this is, the first iterate is of this form. And then given all these differences, just like in quasi-Newton approaches, you update xj plus 1 in the following way, where you have xj bar, which is given here, fj bar is given here, where theta minimizes this. It's a least squares approximation. Okay? And if you look at this more carefully, you'll see that it's of the form xj plus beta fj, and then plus some other terms. So this is trying to get the new iterate in order to minimize the linear version of the residual. So the residual will be, of course, nonlinear, but the linear version of the residual will be minimized. So this is a setting that we used. It's very convenient to write it this way, but initially, Anderson wrote the problem differently. The author of this method wrote the xj bar in this way, where the sum of the mu j's is equal to 1. So it's a combination of the previous iterates again, and this is very similar to what we saw with acceleration techniques or with extrapolation techniques. So in this case, the mu must minimize this norm subject to this constraint here. So it turns out that actually, there are some relations with extrapolation type techniques. Don't want to go into details, but Anderson himself was very much influenced by extrapolation techniques. In one of his papers, he just mentioned this general approach of extrapolation. By the way, Anderson is really a mathematician who did work in physics. His paper appeared in a physics journal, but he did a lot of these methods are used by physicists. His method is very popular. It has been very popular, and it's become more popular now in a different area, but it has been very popular in physics, and specifically in what is called the self-consistent field iteration, where you have an iteration, just a fixed point iteration. It's very complex, that you try to accelerate. So before him, there was a paper by Opaleษ์, which did exactly the same thing. Actually, it's not quite before him. It's about the same time, or maybe Opaleษ์was even afterwards. But the two things were not known to each other, but people realized later that the methods were essentially the same, under some conditions, obviously. Now let's look at the relation between Anderson and other techniques. So this is something that's satisfied by what is called the multi-second type approach. So if you recall what I did for the Jacobian, this thing here, or this one, what we do is you update the Jacobian, the inverse Jacobian. This is the inverse Jacobian that we're updating from the previous one by adding a rank 1 term. Instead of adding a rank 1 term, we can now think of adding a rank m term. So you have, instead of, it's a block method essentially. Instead of having one vector at a time, you do a set of vectors, and you update the Jacobian in that way. That is called a multi-second method, okay? And it was introduced in 1984 by Lewis and Vanderbilt. These are physicists again. And it was worked on by Ayert in 1996, who discovered that these methods were very much related to Anderson acceleration. So Anderson acceleration could be put exactly in this one, and I'll show you in a second what this does. So you have the second requirement, just like what we had before for the second requirement. Now it's a multi-second requirement, and you have a no-change condition, very similar to what we had before, but now it involves a whole subspace. So now this is set in algebraic terms, but in those papers it was set slightly differently. And then you get this update. So you update the inverse Jacobian from the one m steps before by a formula like this. And here is the update. And if you set this thing here to be the very previous, essentially the initial approximation to be minus beta identity, you get exactly Anderson acceleration. It's exactly the formula for Anderson acceleration, which is remarkable. So this was shown by Eert in 1996, and we had a paper that expanded on this a little bit in 2009. So this is just to show that there are formulas that show that this is just to show formulas that give you explicitly xj bar and fb bar, and they will resemble some things we will see in a second. That's why I'm showing them here. There was a paper by Walker and Lee in 2011 that shows the equivalence with GMRAS in the near case. Now let's talk about specifically what I had. This is a background that I gave you. Now I'm going to talk a little bit about methods we developed based on GCR. So we wanted to start with an acceleration in the linear case and extend it to the nonlinear case. And these are Krylov subspace methods that are well known. What we're looking at specifically is generalized conjugate residual. All right. Why GCR? Why not GMRAS? Well, this has to do with one of the issues I mentioned earlier. That is that in these inexact Newton methods, you need to evaluate the Jacobian in some arbitrary locations, and that's really a limitation. So the nice thing about this GCR is that you have X, the current iterate is available to you every time. So you can do things that you could not do with things like other Krylov methods that generate the basis and annul the basis, etc. So here's the general GCR approach. You can see that you have an update just like the conjugate gradient. This is similar to conjugate gradient, not quite the same formula here. But what's important is that the P that you define here, the new direction of search, is defined by combining the most recent residual with the previous PIs in such a way that the APIs are orthogonal, not necessarily orthonormal, but not orthogonal. So you enforce orthogonality of the APIs. It's a very simple procedure. And then with this, you're guaranteed that the residual will be minimized. So that's all that you have to know. That is that this way of generating the PIs and the alpha will guarantee that you have a minimal residual approach. So equivalent essentially to GMRAS, for example. So there are variants, GCR of K, which is restarting, and then truncated GCR, which is essentially, instead of orthogonalizing at all the previous iterates, I'm going to take only a few of those. And then so you truncate the orthogonalization process. It's like, it's like IOM or so. Those things are very common because you don't want to keep all the directions. It's expensive, both in terms of memory and in terms of computations. So this is truncated GMRAS, truncated GCR, and you can see that you have a restart dimension as well in here. So that's the formula for the restart, for the direction PJ. So GCR of K was defined and studied by Eisenstadt, Elman, and Schutz in 1983. The paper, I think, appeared in 1984, and that's equivalent to GMRAS of K. But truncated GCR was actually initially developed van Winsum in Winsome, I guess it's the pronunciation, in 1976, specifically for problems in reservoir simulation. So it was not really that well known, but this paper developed essentially GCR of K, the truncated GCR. But I will refer to the method as truncated GCR instead of orthomin. So properties of this method, the linear case still, okay? So if you call PK these matrix of the directions, RK the matrix of the residuals, and you call P VK the matrix APK, then these are properties that were shown in that paper. The residuals are semi-conjugate, meaning that RJ is orthogonal to the previous ARIs. So when the matrix is symmetric, you get residuals that are conjugate, and that is a method that leads you to a method developed by Stiefel in the 50s called the conjugate residual method. It was not it's an obscure paper, it was not that well known. Not many people use the conjugate residual method, but it's similar to conjugate gradient. But it generates residuals that are conjugate. So then this matrix is lowered by a diagonal. It's not very, it has some consequences, etc. So, and then the nice thing also is that you cannot get a breakdown unless you get the exact solution. Okay. So these are additional properties. I really would like you to look at this specific formula here. xk plus 1 is x0 plus bk by vk transpose r0. Again, you can see that you have some sort of approximate inverse in here that's used, okay? And this has some interesting properties. This bk matrix bk here, it's a low rank matrix, it's k rank k matrix. It plays the role of some sort of approximate inverse. In a sense of, it's still a rank K matrix, but there are some properties here that resemble the more Penrose properties for the pseudo-inverse. For example, ABK is a projector. It's an orthogonal projector. Okay, this is very similar to what you see in pseudo-inverses. So I'm going to skip that. I'm going to the inexact Newton GCR. So this is what people did in the past. You could use, so this is inexact Newton with GCR. You could use that. And if you impose something like this and you have impose some conditions on the eta j's, then you get global convergence. It has been studied very heavily in the 80s. In particular, there's this paper by Denbo, Einstein, and Steinhaug, 83, etc. So that is not what I'm going to do. And instead, try to take a look at the multi-second approach that we have looked at, and we can benefit from insight from the Anderson approach. So these vectors that you, as you recall, the vectors A, P, J, M, or the APJ, the previous APIs are orthogonal. That's one thing that's generated by GCR. So in the non-linear case, we can still use this basis. But A is some Jacobian. We don't really say explicitly that Jacobian at this iterate or something like that. So I'm going to specify in a moment what that would be. So in inexact Newton, this A is the Jacobian at the initial iterate, and you're generating this basis, and you can get one iterate, and then you repeat the process. So let's consider specifically these two bases now. Thus you have the previous PJs, which are essentially there's no specifics about this. There's no orthogonality. What happens is these are the ones that are orthonormal. This is because they're the J times, so these are the J xi times pi. And those are orthonormal. So now I have two sets of vectors, and they're coupled, the PJs and the VIs. And they're very similar to what we saw here. And these are the same, the PIs I had, and the VKs are those vectors that I had defined earlier here, so the APK. Except that in our case now, the A is no longer a matrix that is fixed. That's the only difference. So this vector, these VJs that you see here, they're defined this way. As you can see, the Jacobian changes at every step. So now I'm going to use the formalism I got from Anderson acceleration and quasi-Newton to write this a little bit in a strange notation. This VJ is this J times PJ, but meaning that this J changes with every vector. And then the main idea is really simply this: write xj plus 1 in this form, where yj minimizes this. That's it. And now the VJs will be, PJs will be generated exactly as was done with GCR. And that's the algorithm right here. So I'm going to spend a couple of minutes on this one. So this is the algorithm. Instead of having one alpha, remember in the GCR we had one scalar. Now we have to use the whole basis. So we do projection. This one used to be linear residual in the GCR. Now we have it in the nonlinear form. But recall that I might actually use this in a second. I'm going to say that later. So we have to, in order to gain in time, I would like to keep this possible as a possibility. They could update the residual in this way, linear way as opposed to nonlinear way. And then the whole thing here is just to generate a new direction exactly as was done in the, and this notation is not very clear, I realize that, but exactly as was done in GCR. So you generate residuals, vectors, PJs that are A, so that the corresponding J times P are orthogonal, A times P are orthogonal. And that's it, then you restart. Okay, so that's the algorithm. So there are a couple of properties. This is a linear residual, and if you take the difference between the linear and nonlinear residual, this is linear residual, then you have some nice, a couple of nice properties here. The RJ tilde, so first of all, this is by the algorithm. This is exactly what the algorithm does. This is not this by construction. This one is something you can show. The RJ tilde is orthogonal to VIs. That's because of the way this X is defined. And then we have a minimization property that's satisfied here. There is some, the reason, what I wanted to show is this particular expression here, because it will show that there is some sort of, descent direction at that point. So that is, in fact, shown in the next property. But these are not really, so you can show some results that show the difference between the linear and nonlinear residual is small. Then there is, these are properties that you can read in detail in the paper. So there's some properties you can show. One that I want to emphasize is that you can show that there is a sort of descent direction. It's not quite proven, except because this term may not be necessarily positive. So this term is definitely positive, so we have a minus sign. This whole thing is negative, which means that the gradient, the direction dj that you use for updating the solution has a negative angle as a negative cosine with the current gradient. Except that this term here is not necessarily proven to be positive yet, but you can see that in general you have there are some formulas where this doesn't exist actually. So in some situations this will be a descent direction. And you can, by the way, you can also check that this is something that's easy, economically feasible to check. So next, the millisecond property. This is something that I mentioned a few times here. We have this matrix is the approximate inverse Jacobian, essentially, and it satisfies very similar properties to those that you see in millisecond methods. So you can frame it in the form of multi-second method. But the difference between Anderson acceleration is you can add convergence strategies. And that's something that is a very important consideration. You cannot do that easily with Anderson. Okay? The other thing that's important here is Anderson does develop a Jacobian, approximate Jacobian, based on differences between fj plus 1 and fj. But those are not necessarily, so xj plus 1 and xj are not necessarily close to each other at the beginning. So the Jacobian you're approximating, the approximation of the Jacobian you're getting is not very good at the beginning. So this is an advantage because you can compute that accurately. That's a very big difference. okay? In the inexact Newton methods, not inexact, in Broyden type approaches, in Anderson as well, you're doing an approximation that is very rough at the very beginning of the process, because xj plus 1 and xj are not close. So you're using something, a linear approximation where you shouldn't. So then I'm going to say that you can say there are some situations where Anderson does very well, and we tried it, for example, for Picard iteration, Navier-Stokes. It does quite well. It's very hard to beat. So, but the question is, can we implement Anderson in this form, in the form of GCR? The answer is yes. I'm going to skip details here, and I'm going to just show you a few experiments to conclude. So this first experiment is really just to show the importance of symmetry and other things, and in particular, the importance of adaptive version. So this is the nonlinear, it's a nonlinear eigenvalue problem called the Bras-II problem. It's fairly easy to solve. It's not a very difficult problem, unless you take a lambda that's not good. So we tested these methods, and we tested what we call an adaptive gradient. So if you were careful in the algorithm they showed, there are actually 2 function evaluations per step instead of 1. So it is wasteful. The reason why you have 2 function evaluations is because you're in the usual method, you compute the residual from the previous iterate. So you have a linear approximation of the residual. So we thought of doing something in between. So explore the linearized version, so the linear update of the residual when you're close to the linear regime. You can cut the number of function evaluations by half in that case, and come back to the nonlinear case when necessary. So we have sorry, oops, going back the wrong way. So this is nonlinear residual, and if you recall, this is linear residual. It's updated from the previous iterates, the previous iterate and the yj. And then you define what you have this measure, and when it's close to 0, you're fine. It's a linear, close to the linear regime. So you use that formula, and once in a while you check this value, and if it diverges too far from 0, then you go back to the linear regime, nonlinear regime, and then you can see here if you do this, what you see right here is a method that uses entirely the linear updates, and it fails. Okay. But if you do an adaptive version, then you get something that works nicely. So this is NLTGCR adaptive, nonlinear. Totally nonlinear is here, and adaptive is here. You can see that the nonlinear version uses twice as many function evaluations as I mentioned earlier. So you cut down the number of evaluations by half, and you get a very similar convergence curve. And this is iterations versus function evaluations. So the number of iterations is quite similar. We have here something that shows that symmetry helps. You can see this curve here is with only one vector. So the m in the number of vectors you keep, that's a very important number because it shows you, it relates to the cost of the iteration. So that is, you can see here that m equals 1 works quite well. So it's like using the conjugate gradient, essentially, in this case. And compared to the other approaches, Nesterov, we have Anderson acceleration, which is showing up here. We have, this one is the nonlinear conjugate gradient, Fletcher-Reeves. And this one here is Nesterov, and then we have Newton CG, which is a different approach. Okay, so this indicates the importance of symmetry, because we know that in this case we're near symmetric. The Jacobian is near symmetric, and you can use something like a conjugate gradient. We have a short-term recurrence, which is essentially using m equals 1 in our case. Okay, so now this is a slightly harder problem. The Lennard-Jones potential. So you're trying to optimize minimize essentially the potential energy based on this formula here. And you can see this is a harder problem. You can start from some iteration and you get to the final one. I want to show you just very briefly some of the things you get. Here, Anderson doesn't work very well. It works only if you take a very, very small, you have to define the function very specifically, otherwise it doesn't work too well. It will diverge, because you can think, this is a very dangerous kind of thing to do, right? Power 12 in the denominator. If xj and xi are close, then it blows up. So you have to be very careful how you define the function that you're trying to minimize in Anderson. So this is essentially the convergence curve in the situation. In fact, there are other curves that indicate very poor convergence for Anderson, or it blows up. Here you have Nesterov, which is right, Anderson acceleration is here, etc. And then finally, we just did recently some work on trying to use these for graph convolution networks. This is essentially optimizing certain function, and I'm going to skip it, but say that we're really looking now at applying these methods for machine learning. And they just seem to work quite well in some situations. You have to adapt to the stochastic context, because we no longer have a function that's fixed and so on. So these are a few references. I will leave these here if you're going to take a look at the paper. I will post this paper, this talk on my website, and I will leave the concluding remarks here. The only thing I want to say is that our future work is we're looking at adapting NGCR to non-smooth context, specifically stochastic context for machine learning. I'll answer any questions you have. Stop here. Thank you. You don't have a microphone?
Question?
Yeah.
Thank you very much for this thorough review of the inexact Newton methods. That's the way I perceive it. Now, ask you to comment on two issues pertaining to what I call the tyranny of the Jacobian. Number one, the effect of the inexact Newton method, I'm talking about nonlinear problems, or the convergence of the overall procedure. Number two, can you compromise on the quality of the eigenvectors of the Jacobian in case we need to deal with stability issues, close to singularities especially, which is the case for the Bratoux problem you just mentioned, past the turning points and things of that sort. We need to know the eigenvectors with good accuracy in order to do stability, reliable stability evaluations. These are the two issues I want you to comment, please.
Yeah, thanks. Interesting, very, very good questions. So I'll answer the second question first. When it comes to stabilities and things like when you have Jacobians that could explode, etc., people utilize line search type techniques, where it's very, very important not to go, not just use the whatever iterate you have, but be very careful in backtracking to get a solution that does not, minimize, does go down. For example, the gradient has to go down. So that's very important to use this line search, or what is called global strategy techniques. Global strategy meaning you have techniques that will ensure convergence by doing like line search or trust region techniques and things like that. And then for the first question, that was to do with the convergence, right? Yeah. So there's a lot of things with inexact Newton methods. A lot of things have been developed to prove convergence under some conditions. And that, in fact, for inexact Newton, it's actually easier to show convergence, because if you impose some conditions on the residual, the current residual, you have to impose a certain decrease of the residual, then you can show convergence in a certain form. For the other methods, it's a little harder, but it's still tied to the line search. So everything in here is based, for the convergence, is based on line search and trying to make sure that you decrease the function. And there are very elaborate techniques that do that. I'm not entirely an expert in this area, by the way, but there's a lot of people in this room who know, all these techniques that have been developed in the past. It's quite a few techniques. Yeah.
When you use Rato example.
Which one? That one? Rato, yeah, for Rato problem, yeah, sorry, yeah.
You showed that Nesterov and BFGS algorithm converge.
Yeah.
So this example, for example. So if you use only reduced rank extrapolation, it will accelerate the convergence with a very small amount of cost.
Yeah, that's right. I think this kind of actually, for the Prado problem, so if you do extrapolation for Bratu, that's what we mean, yeah. You can get something of a similar. Yeah, right, yeah. I think for the Prado problem, you actually could do probably better than what's shown in here. For the extrapolation methods will work well for this problem. But, the disadvantage of extrapolation techniques is precisely that you have no access to the function. And therefore you cannot do things like line search, for example, to show global convergence. So you might get very nice performance in some situations, but it might blow up your face in other situations. It's very, so it's, in all of these methods, you can always find something that works well for a problem, but you've got to be careful for the general situation. Yeah. How do you define the conversion in which case?
In practice.
In practice, yes. Yeah, so there is a difference between practice and theory. I'm glad you asked that question, because there is a very big difference between practice and theory. In practice, you only look at, so you have basically a couple of criteria you use to show, to make sure, for example, that the gradient decreases, and you can look at the norm of the gradient as one approach, and then the direction between the gradient and the direction of search also makes a difference. So there's two things that are used as criteria to define a satisfactory point that you have for convergence. So, but it's really a mixture between practice and between heuristics and theory.
Okay, thank you.
All right, thank you.
Just to mention that the coffee break is near room A. Yeah.
Θα έχετε και στις 3 παράλληλα. Όχι, και στις 3 αίθουσες παράλληλα τώρα. Κάτω χρειαζόμαστε ένα λάπτοπ στο Βρακόπουλο, γιατί κόλλησε το άλλο που είχαμε εμείς. Και το αφαίρεσα. Το Αργυριάδης είναι εντάξει, μου δώσαν και 3 παρουσιάσεις. Τώρα να ανοίξω και αυτό γιατί τα έκλεισα, γιατί νόμιζα ότι θα συνεχίσετε κάτω. Στο Βρακόπουλο, ναι. Ελάτε για την παρουσίαση. Ναι, έλα.
Υπάρχει κάποιος φάκελος, πού το βάζουμε?
Όχι.
Στον desktop.
Συνήθως βάζω στο δεξιά.
Από εδώ.
Από αυτή την πλευρά όμως.
Αυτό τι, εδώ μπαίνει.
Όχι από εκείνη, βάλτε το καλύτερα από εδώ.
Θύρα USB είναι αυτή.
Ναι.
Αν νόμιζα ήταν κάτι άλλο, το είδα μεγαλύτερο.
Ξεκίνα και την ομιλία.
Εντάξει.
Χρειάζεται να τα αντιγράψουμε στο λάπτοπ ή απλά μπορούμε και την
Καλύτερα να τα
αντιγράψουμε τώρα.
Να κάνεις και έτσι όπως το λες εσύ.
Ναι.
Μια χαρά είναι. Απλώς μην κολλήσει τίποτα και το άλλο κάτω στο Βρακόπουλο κόλλησε.
Άσε και τα μέσα. Φρασάκι, δεν είναι και εμπιστοσύνη. Θα σας αντιγράψουμε.
Κόπη.
Το βρήκες?
Το βρήκα. Περίμενε. Paste.
Πήγαινε αριστερά.
Πού πήγε
το δεύτερο.
Αυτό εδώ.
Για πήγαινε αριστερά.
Το βάζω εδώ κάτω, έτσι.
Όπου θες βάλω. Αρκεί να είναι από δεξιά.
Κάτσε λίγο τώρα να το δούμε αν τα σύμβολα είναι εντάξει και φεύγουν. Ναι. Αχ, κάτσε, κάτι σύμβολα δεν βγάζει. Περίμενα να πάρω το PDF. Ένα λεπτάκι. Είναι το PDF το αντίστοιχο γιατί δεν μου βγάζει κάτι σύμβολα. Δεν μου βγάζει κάτι σύμβολα. Το R3 της, ναι, μου χάλαγε το R. Αυτό τώρα πώς γίνεται full?
Και δες το κάτω δεξιά.
Αυτό εδώ. Το έβγαλε. Εντάξει, μια χαρά, ναι, οκ. Άρα λοιπόν, περίμενε τώρα. Σβήνω το PPT. Και μένει το PDF, ωραία. Φεύγει και αυτό. Κάνουμε και eject από εδώ. Ωραία, έτοιμος.
Ναι, ναι. Πάρε με καμιά φωτογραφία να τη δείξω στη γυναίκα μου. Να μην φαίνεται όμως ότι δεν έχει κόσμο από κάτω, πάρει να της λέει όταν είναι γεμάτη η αίθουσα. Αυτό.
Elle me dit, on n'a pas de programme. Bah, fais-le, connasse. Elle me dit, il n'y a pas de programme. Bah, je dis, ouais, bah, vas-y, bah, il fallait en imprimer un, connasse.
Oh.
Is it okay or no? No?
This is bad.
Okay, okay, don't worry, it's okay. Vicky, maybe you can talk to the microphone. Thank you, Vicky. So, good morning, everybody, and I'm very happy to be here and welcome to this NASCA 23 conference. So, I wanted to say some words about Professor Dr. Petridis. Actually, I met, here's a photograph of him. It's always a pleasure to see his photograph. So we met him during a workshop organized here in Athens, and we were impressed by him, really, because we felt that he was so passionate about mathematics, and not only mathematics. I'm drifting a little bit away from the text. He could talk you hours about music, about classical music, about jazz music, literature. Is fluent in many languages, and it was really an honor to meet him. So, as you may know, Mr. Petridi completed his PhD in 1946, if I'm not mistaken, in Sweden. And since then, he maintained this passion, very vivid, although he had professional duties which he had to attend. But he didn't stop research in mathematics, and that is something that is very impressive. And also, it's an inspiration about, it's an inspiration for all of us. So, to make a long story short, the message would be that mathematics are not, and research are not only about having a nice career, a coveted position in a university and academy. It's about passion, and I think it's the message that we have to bear in mind. So we think about him. I know he's more than 100 years old, which is admirable, and so it was just a few words to tell our appreciation. So thank you all. Thank you.
Ξέρετε ποιο αρχείο είναι? Ναι. Τέλεια. Ναι. Τέλεια. Art. By
Thank you very much for the introduction. And I would like to thank particularly the organizers for bringing this conference to my attention, and I'm happy to present this work here today. So let me again repeat the title. It's a parallelizable algorithm for the inversion of matrices with simultaneously diagonalizable blocks. We'll explain this notion in the first slides. Importantly, let me mention that this is a joint work with Dimitris Lazaridis. Dimitris is a PhD candidate at the Aristotle University of Thessaloniki, and Konstantinos Draziotis, who is a colleague. He's an assistant professor in the same university. We are all in the School of Informatics of the Aristotle University. So this is the outline of the talk. It will be about an efficient algorithm for inverting a particular type of matrices, which, however, is encountered in many applications, and we'll speak about applications in the last part of this talk, since this is a session on mathematical modeling. So we'll have a block matrix. It will be partitioned in blocks, and this block will have the property to be simultaneously diagonalizable. The algorithm we will follow to invert such a matrix will be to diagonalize first each block, and then to develop and apply a similarity transformation algorithm for inverting the matrix with diagonal blocks, which stems from the eigenvalues of each block Aij. We will determine the computational complexity of the inversion, then implement a parallelization of the developed algorithm, and finish with some applications in mathematical modeling and standing numerically obtain CPU time efficiency and accuracy. So some definitions first. Definition 1 and 2 are very well known. It's about when a matrix is similar to another matrix and when a matrix is said to be diagonalizable. Let me emphasize more the last two definitions, which are important in the structure of the matrix we will analyze. So two diagonalizable matrices A and B are said to be simultaneously diagonalizable. Either exists a single similarity matrix S, such that S minus 1 AS and S minus 1 BS are both diagonal. So we have a single basis for the representation of the linear transformation. Okay, and we can also extend that and define a simultaneously diagonalizable family as a family where there exists a single non-singular matrix S, such that S minus 1 AS is diagonal for every A in the family. So this is the structure of the matrix. It's composed of blocks Aij. Now we have two main parameters in this talk, M and N. N is the dimension, is the order of each block Aij, and M, or M square, is the number of blocks in this matrix. So each block row has M matrices, and each block column has M matrices. Now the core steps of the inversion algorithms will be first to block diagonalize matrix A, and then apply a similarity transformation algorithm for inverting the block matrix stemming from the eigenvalues of the blocks. The first part is the block diagonalization. So this is quite easy to do. We apply that every block is S minus 1 times, or as written here, S times lambda ij times S minus 1, where lambda ij are diagonal blocks. They have the eigenvalues on the main diagonal. And if we do that for all blocks, then we obtain a block diagonalization, as is shown in this slide, where the lambda ij matrices composing this block matrix in the middle of this diagonalization. In each of these matrices, on the diagonal lie the eigenvalues of the blocks. Now, if A is invertible, then the inverse A minus 1 has the block diagonalization, which is shown here, where the middle matrix composed of blocks Lij is the lambda to the minus 1. So it's the inverse of the matrix lambda composed of diagonal blocks. So in order to invert matrix A, we have to invert the matrix to diagonal blocks lambda, composed of the blocks lambda ij. Okay, now if one looks at the graph of lambda, and we have also an example in the next slide, the graph is composed of n disjoint subgraphs, each with m nodes. So since this matrix has only the blocks lambda ij, and each matrix is diagonal of these blocks lambda ij, then if we connect the elements to each other and compose a graph of this matrix as shown here, we have only certain connections, and all the other connections are eliminated because this matrix has a large number than zeros. Now, if we form the E-vectors, the E-vectors are the standard base of the Rm times n of space, then we see, for example, that if we number particularly the elements, and I'll show you an example in a minute, then we have that, for example, these red elements, these red nodes of the graph, are connected only as follows. We have 1, n plus 1, 2n plus 1, and so on, until m minus 1, n plus 1. So we take these base vectors E1, En plus 1 as follows. Let me show you an example before doing the algorithm. We have this example on the top part is matrix lambda. So we have m equal to 3 and n equal to 4. N is the dimension of each block, and m or m square is the number of blocks composing this lambda matrix. So if we build the graph of this matrix and see the connections, so eliminating the zero elements of this matrix, we are left that we have only these base vectors, standard base vectors, E1, E5, E9, and so on. For example, E1 is given due to this element, E5 due to this element, E9 due to this element, and so on. Now, if we do a permutation by building these vectors and building this P matrix, this P comes from the word permutation, then if we apply P times lambda times P transpose, we transform the matrix lambda to the matrix lambda prime shown here. So this matrix, instead of having these 9 blocks lambda ij composed of diagonal elements, we build the matrix lambda prime, which has 4 blocks composed of full elements. Now this is important because if we want to invert matrix lambda, we can equivalently invert matrix lambda prime, but it is easy to invert matrix lambda prime because we have to invert independently all the blocks, the full blocks composing the main diagonal, the main block diagonal. Okay, so this is the main core of doing the similarity transformation algorithm. We denote by EI the standard base of Rm times n. We build this permutation matrix, as we saw in the specific example of m equal 3, n equal 4. And by doing this permutation P times lambda times P transpose, we reduce the matrix lambda, which is composed of diagonal blocks, to the matrix here, in the right-hand side, we denote by lambda prime, which is a block diagonal matrix, in the sense that we have non-zero blocks only in the main block diagonal. These are denoted by lambda 1 prime, lambda 2 prime, and so on, lambda n prime. Okay. Now, having done that, it is quite straightforward to invert this matrix lambda prime. If we invert all of these matrices, the full matrices lying in the main block diagonal, for example, lambda 1 prime, the inverse of this, lambda 2 prime, the inverse, and so on, then we can subsequently apply the inverse similarity transformation algorithm, as shown here, and obtain matrix lambda to the minus 1, which is the final outcome, the desired inverse matrix we will need to have in order to invert our original matrix A. Now let's go on to study the computational complexity of this inversion scheme. It is composed of 4 elements, let's say the complexity is denoted by C. It's composed of 4 summands of 4 elements. The first is C underscore S. It's the number of, let me say that as is written here, by complexity we mean the total number of required scalar complex multiplications. So for C subscript S to compute the matrix S and S minus 1, we need 2n cube multiplications, because this is an n by n matrix. So we have n to the power of cube, and since this is, we need to do this twice, we have 2n n to the power of cube multiplications. Now, the other elements, let me just show the elements and then we will go to the computation. It's the complexity to do the block diagonalization of matrix A, the complexity to do the inversion of matrix lambda to build matrix lambda minus 1, and finally the complexity to do the inverse block diagonalization sim. These are denoted by CBDA and CBDA minus 1. Okay? Now, the complexity of doing the block diagonalization is m to the power of 2, n to the power of 3, because we have m square blocks, and in order to block diagonalize each one, we need n to the power of 3 multiplications. So this is the overall complexity, and it's the same complexity to do the block diagonalization of the inverse matrix. So m to the power of 2, n to the power of 3. Now, in order to invert matrix lambda, this is actually the primary contribution, the main improvement in doing less computations. We need n times m to the power of 3. Because, let me just show you the previous slide, we need only to invert these matrices, and each of these matrices is n times n, and all these are m in total. So the number of multiplications we need to do are m times n to the power of 3. So after all this analysis, we end up with this expression, which gives the overall complexity with respect to inverting matrix A. Now, one of the main contributions of this talk is that we can do a parallel sim, we can parallelize this algorithm, and it's shown graphically the main idea here, since the main contribution, the main part of the algorithm lies in finding the inverses of these matrices lying in the main block diagonal, so denoted by lambda 1 prime, lambda 2 prime, and so on. We can assign these calculations to a different processing unit, denoted here by thread 1, thread 2, and so on. So since these are independent calculations and independent computations, we can build a program and assign each of these inversions to a different processing unit, and in this way speed up significantly the calculations. Now, this is the strategy we followed to implement the parallelization algorithm. Let me briefly give some details. We used OpenMP API for shared memory parallel programming. The algorithm was written in Python using the library Numba for automatic parallelization. We produced the results by using the Aristotle University of Thessaloniki high-performance computing infrastructure and resources, and we want to acknowledge this infrastructure given to us. Also, here are the details of the machinery we used for executing the parallel algorithm. Okay, now these are the following 4 or 5 slides show some results of numerical experimentation. For a reference, we used the LU algorithm, which does not exploit anything from the structure of these matrices. So this is m to the power of 3, n to the power of 3 calculations. The LU algorithm, the execution time is in these slides. The LU algorithm is this curve, the top one. And here in the horizontal axis is the values of m. M is how many blocks lie in each block row. And this diagram is for n equal to 100 constant. Now, as we go down, we increase the number of threads. For example, this last curve, which lies at the bottom of this diagram, corresponds to 128 threads by means of implementing these independent inversions that we have seen in the previous slide. This is one thread. One thread means serial processing, so we did not do any parallelization. And then we go to the power of 2 threads, 4 threads, and so on, until 128 threads. Now we can see that the main speed up is achieved from 2 to 4 or from 4 to 8. And then as we increase the number of threads, we have some improvement, but it's not that significant as for the improvement observed in the first, for the first number of threads. Now, these are the same data, but depicted in a different way, because in the horizontal axis we have the thread values, the thread numbers that we use to implement the parallel processing, and on the vertical axis is again the time we needed to do the calculations. Here we have a different setting, because we kept m equal to 100 constant, and we changed n. So these are the values of n. N is the dimension, the order of each of the blocks, and m is how many blocks we have in each block row. Again, the concept we follow to create this diagram are similar. So here is the LU algorithm, and the bottom line is 128 threads, while this blue line is one thread, which means serial processing and so on. And as we go down, we increase the number of threads until 128. And this is again for the same data, m equal to 100, but now we plot it with respect to the values of the threads used in the parallel processing for increasing values of n as a parameter in this plot. Now, what we did here is we again applied the algorithm for these values. Now, n times m is the total number of elements in each row or in each column equivalently of the matrix. This is for n times m equal to 2000, 3000, 4000, and 5000. And in each of these plots, we have either kept n to be constant or m to be constant each time. And we see, for example, the differences with respect to keeping constant either the number of blocks or the number of elements in each block with respect to the merit, to the speed up we achieved in the parallel processing algorithm. Now let's come to some applications in mathematical modelings, also to answer the questions that many of you could have. Where can we encounter, where can we meet such type of matrices? We have specific applications when implementing efficient algorithms to invert block matrices which stem from the so-called discrete trigonometric transforms, DTTs. These applications can come from computational electromagnetics, and here is a list of 4 classical methods in computational electromagnetics: method of moments, method of auxiliary sources, the boundary element method, and the DDA, the discrete dipole approximation. And each time when we do a numerical discretization scheme to solve problems in CM, in computational electromagnetics, by means of these methods, we are encountered with matrices which have this type of structures, but now we have some, let's say, specific situation, because these matrices S, which simultaneously diagonalize its blocks, have a certain property. They are unitary matrices. So they are not just matrices which are invertible in order to build the diagonalization. They are unitary matrices. And specifically, these unitary matrices in the group which we have defined as DTTs can be Fourier matrices, Hartley matrices, cosine matrices, sine matrices, and so on. And for each of these type of matrices, the generated matrices A are circulants, skew circulants, Teplitz-Pals-Hankel, and tridiagonal matrices, when the matrix U is in one of these categories. Okay. Now here we can do something better, because we have a certain property of the unitary matrices, and we can find the eigenvalues more quickly. So the complexity which we have shown before, if you remember, it had here a component m to the power of 2, n to the power of 3. But if we have this specific category of matrices, for example, when U belonging to the general class of unitary matrices is a Fourier matrix, then we can find the eigenvalues at the so-called FFT speed. So we can take n log n calculations. And we have a drastic reduction in the computational complexity, and this term m to the power of 2, n to the power of 3 drops to n to the power of 2 times order n log n, because we can do calculations for these matrices at FFT speed. The first term is the same, because the first term comes from the similarity transformation algorithm, and this does not change. It's n times m to the power of 3. And now here we have some specific examples where we calculated the CPU time with respect to m times n, which is the total number of elements per row or per column of the matrix. This comes from the application of the method of moments in the radiation by circular loop antenna arrays. So here the m and n are something very specific for the electromagnetic problem. M is the number of circular loops, and n is the number of basis functions per loop. And we can see again that we have a drastic reduction in the CPU time. Here the black curve is the LU decomposition for m equal to 4, and the corresponding colored curves are if we follow the developed algorithm for different types of matrices and parameters. Here's the second example, again for the CPU time reduction. It's the modeling of scattering by the so-called D-bores, the discrete bodies of revolutions, by again the method of moments. Now n denotes the number of wires, and m denotes the current basis functions per wire. So for example, here we have this picture showing that each of these is called a wire. So the total number of these wires will be the parameter n in the method, while in how many segments, how many basis functions we can take per wire will give the parameter m. And here we have similar types of diagrams. The vertical axis is CPU time, and the horizontal axis is L over a lambda. The small lambda is the wavelength, and the capital lambda is the length of each of these wires. And we can see that, for example, this blue curve is the standard Dirac solver inversion, and this red curve is the developed algorithm imposing this similarity transformation procedure. Also, we can have the pictures we have seen up to now concern the CPU time improvement. We can have also some pictures concerning the accuracy improvement for ill-conditioned matrices. This is a modeling, MAS is called the method of auxiliary sources. So we have an MAS modeling when scattering by layered obstacles. Now n denotes the number of auxiliary sources, and m denotes the number of auxiliary surfaces used to discretize the scatterer. And we can see, for example, let's look, for example, at this diagram. And now this shows the condition number. This is the condition number stemming from the conditional number of the original matrix A, and this red curve denotes the condition number from inverting all these matrices lambda k prime involved in the similarity transformation algorithm. So we see that the condition numbers of inverting these matrices are having much reduced with respect to inverting brute force without doing any exploitation of the structure matrix A. So coming to the conclusions, we have presented an efficient inversion method for an m times m block matrix A with blocks Aij. These blocks have dimension n, each of these blocks, and they are simultaneously diagonalizable. This is the computational complexity of this SIM. We have also given some implementation for parallel processing of this algorithm. And at the last part of the talk, we have presented applications in mathematical modeling, particularly to invert block matrices associated with DTTs, discrete trigonometric transforms. These matrices stem from applications of computational electromagnetics. And with respect to these applications in mathematical modeling, we have shown some numerical results where we exhibited the CPU time efficiency and high accuracy of this developed method. And for these applications of computational electromagnetics, since we have some explicit expressions of the eigenvalues of these matrices, we can further reduce significantly this complexity of the general SIM. Thank you very much for your attention.
Thank you very much for the nice
No, I can't hear. Can you speak louder? I can't hear, I'm sorry. I'm sorry, I can't hear.
GPUs. Have you tried algorithm?
Not yet, no, not yet. We have tried first this SIM. The question is about GPUs, right? Yes. Sorry, I could not hear in the beginning. We have tried this setting to do some parallelization. I don't know, there's no particular reason not implementing GPUs yet.
Will be considerably faster.
Maybe, yes, okay. It's something we can consider, okay. Thank you for the suggestion. Thank you very much. Yes, that's a very interesting comment. I haven't thought about it. That's very interesting. I don't know. This comes from an application of discretizing a cylinder. So when discretizing a cylinder, you have some kinds of symmetries in the blocks. So maybe, but that's a very interesting question, maybe that has to do with the symmetries, the geometrical symmetries of the original problem, the way these matrices are split and these eigenvalues lie. Yes, that's very interesting. I suspect that if we have an obstacle, not a cylinder with not such symmetries, then we would see a different picture. But I haven't done this, okay, so thanks a lot. This is a very good question. This has to do with applications. For example, I don't think there can be a general rule because, okay, for this example, M is the number of circular loops, let's say. This is, let's say, constant with respect to the considered application. But then N is the number of basis functions. So in this example, we need N to be large. But now in a different example, we'll have this D bores. Then N is the number of wires. Now this is the, let's say, constant parameter. And M is the number of current basis functions. So here we need M to be large. So I don't think there is a general answer here, but it depends. When you have a specific application, then you can examine within this application the large N or the large M limits.
Εδώ. Είναι το full. Ναι.
Αυτό το touchpad. Λοιπόν, οκ, ευχαριστώ.
Από ένα σημείο.
Good morning. Thank you very much for being here. I want to thank the organizer committee for organizing this conference. I will present you a mathematical model in order to study the rod-blood cell magnetic susceptibility. This is a joint work with Professor Hadjinicolaou from the Hellenic Open University and Professor Vafeas from the University of Patras. This is... We lost the outline of our presentation. In the outline of our presentation, we'll see our motivation. We'll see our mathematical model, the statement, the solution, and we'll draw some magnetic lines. Later, we'll see our results and some references. It is an undeniable fact that mathematics influence medicine and vice versa. In everyday life also. We can see, for instance, the last years, the effect of the epidemiology in our lives. We can refer to drug design and delivery. We can refer to medical imaging, and in general for diagnostic and therapeutical purposes. It doesn't working. Now it's better. Okay, it's the left. Okay, for instance, we can refer to the magnetic fields. Magnetic fields are usually used in medicine in order to have diagnostic and therapeutical purposes. We can refer to magnetic resonance imaging, nuclear magnetic resonance, magnetoencephalography, and magnetotherapy. Point-of-care devices are frequently used in order to have with low cost, accurate results. Examples of POC devices are the pregnancy tests, the test for detecting SARS-CoV-2, or the test who measures hemoglobin in our blood. Recently, a POC device used magnetic nanomaterials in order to have a molecular testing. Of our particular interest are the effect of the magnetic fields on the rheological properties of blood. It has been proved that the effect before and after the administration of magnetic field, the rheological properties of blood differs. This is a table from Gapinska and Honorata, in which some rheological parameters are presented before and after the implementation of the magnetic field. Let's concentrate on blood. Blood completes a whole circle in our vascular system every 20 seconds. It's a suspension of three kinds of cells, the red blood cells, the white blood cells, and the platelets, within blood plasma. Therefore, it seems that the most important cell is the red blood cell. What does the red blood cell in our body? Red blood cell picks up oxygen from the lungs and carries it to the body, and backwards brings carbon dioxide from the body to the lungs. Since it has no nucleus, it has more room to do this carrying. No, previous, okay. Let's talk about our model. In magnetostatic field theory, in the case where there are not permanent poles, we need a magnetic potential phi in order to have a complete representation of our magnetic field through the Laplace equation, delta phi to r equals to 0, which means that the divergence of the gradients of the function phi is equal to 0. The magnetic field strength vector is defined as the opposite of the gradient of the potential phi. Recently, along with Professor Hadjinicolaou, we developed a model in which we calculated the magnetic field in the case where we have a red blood cell in exposed magnetic field of strength H0. We thought that it would be interesting if we could have a more detailed model, and as we looked closer to the structure of the RBC, we saw that the RBC consists of two layers. One layer is its membrane, and one layer is a fluid domain, which has the cytoplasm. And therefore, a more detailed description would be to have a model in this figure, where spaces V2 and V3 are the red blood cell, and space V1 is the outside of the red blood cell. Specifically, space V2 is the membrane, and space V3 is the fluid domain. This red blood cell is embedded in a magnetic field of strength H0, which forms an angle A with the major axis of the red blood cell. In order to have our field, we need to calculate three potentials, phi1, phi2, phi3, for each one of our domains, and therefore the Laplace equation must be solved. This is the far field condition for the function phi1. This is the continuity condition of the potentials between the three domains, where S1, S2 are the surfaces of the red blood cell and the fluid domain of the red blood cell. This is the continuity of the normal vectors with respect to magnetic permeabilities M1, M2, M3. In order to solve a problem like this, we need to choose the appropriate geometry. In order to do something like that, we choose the appropriate geometry as the coordinate surfaces matches with our particle. The red blood cell shape is a biconcave disk, and therefore the appropriate shape would be an inverted prolate spheroid, which means that we have to use the inverted prolate spheroidal geometry, in which every point x1, x2, x3 in the Cartesian coordinates is connected with the modified inverted prolate coordinates tau, zeta, and phi through these relations. You can see in the figure in the right of the slide that when phi is constant, we have the plane. When tau is constant, we have the inverted prolate spheroid, which more clearly you can see it here in the left picture. And in the right, we can have the rotation cyclids, which comes when z is equals to constant. Therefore, we need to translate our problem to the inverted prolate coordinate system. The three first equations are the Laplace equations in the three domain. Domain V1 is expressed when the parameter tau, the variable tau, takes values between 1 and tau 1. Tau 1 expresses, the equation tau is equals to tau 1 expresses the surface of the RBC. The second Laplace equation is in the region between tau 1 and tau 2. The equation tau is on tau 2 expresses the surface of the fluid domain of the red blood cell. And the third equation stands when tau is in the interval greater than tau 2. The fourth equation is the transformed far-field condition. The next two are the continuity of the magnetic potentials, and the last two are the continuity of the normal vectors of the magnetic potential with respect to the magnetic permeabilities. In order to do something to solve the Laplace equation, we have to calculate the Laplace operator, which has this form. When we have to solve a PDE equation, our first attempt is always to apply separation, simple separation. This means that in our case, function phi has to be written as a product of three variables, tau, zeta, and phi. And if this substitution in our Laplace equation comes up to three ordinary differential equations, we have solved our PDE. In our case, this doesn't work, and therefore we proceed with the so-called R separation of variables, where in the previous notation, we moreover will use a factor of 1 over r in our function phi. And if this comes to three separate equations, we have three separate ordinary differential equations, we have the solution. In our case, we have a R separable form of the potential, where R is the Euclidean distance of the inverted Polaris spheroid, which is 1 over SQRT of tau tetragonal plus z square minus 1. And in this expression, the PNM tau, QNM tau, and Z, of course, are the associated Legendre functions of the first and the second kind, respectively. We have to notice here that the variable tau takes value greater than 1, and the variable Z takes values in the interval from -1 to 1, which means that if we take into account that the Legendre equation is of equation 5 in the slide, the orthogonality condition of the Legendre equation stands in the interval -1 up to 1. We have to see that the value Z the value tau in this slide doesn't form orthogonality conditions, and we have to use orthogonality conditions only for the Legendre functions of the variable Z. It's stuck again. Therefore, since we have the solution of this problem, we have to apply the solution in our three functions phi. These are the form of the Legendre functions in order to have an image to what exactly does every one of these means. You can state your concentrating 12 and 13, which is easy to recognize the differences in the two intervals of when absolute value of x is larger than 1 or smaller than 1. Let's start our calculation. For the potentials, all the three potentials stands the same notation. When z equals to 1, we have singularity of the Legendre functions of the second kind, so these functions have to be excluded. Moreover, the potentials are even functions, and therefore the sinus m phi must be excluded also. Therefore, phi1 has this form, and we have to calculate the constants a and b in order to have our potential. First step is to rewrite the far-field condition. We substitute phi1 and for the first term and the second term x1, x3 from the inverted Polaire coordinate system. We have this kind of function. This is equivalent to the far-field condition. We have multiplied it with the sqrt tau square plus z square minus 1 in order to have the ability to apply recurrency relations for the Legendre functions. The recurrency relations for the Legendre function is this 4 that we used in our calculations. And applying this to the left-hand side, this is a part of the left-hand side of our far-field condition. Moreover, if we apply the left equation for the 1 over sqrt tau square plus z square minus 1, and the recurrency relations again, we can have the right-hand side of our transformed far-field equation. And therefore, using orthogonality conditions, we have the constants A and B calculated, and the function phi has this form. We have put the square root under phi 1 in order to, it's more nice, the result in this slide. Okay, potentials phi2 and phi3, as I mentioned before, have the same notation. Therefore, C, D, E, and F must be calculated. We have 4 boundary conditions to express. The first boundary condition for the continuity of the outside of the red blood cell and inside the membrane is phi 1 equals to phi 2 when tau is tau 1. Applying the orthogonality condition, we come up with these 3 relations, 26, 27, 28. Moreover, using the same procedure for the second boundary condition, we have 3 more relations, from which each we can have 29, along with 26, we have a system of a linear system of 2 unknown variables with 2 equations. This, the same happens to 30 and 28, and 31, 27 and 31 to 28. Therefore, you have calculated oral C and D. Using the same methodology, we can calculate E and F constants from the third boundary condition and the fourth boundary condition. And therefore, the final solution of our problems come up with a series expansion of the functions of the 3 potentials, phi 1, phi 2, and phi 3. Next step in these cases is to draw some magnetic lines. Whenever we do something like that, we first approximate our solution with using only the first term of the series. This is the magnetic lines that came up using the values for the potentials 0.5, 1, 2, 3, 4, 5, and their negatives. We have used for the inverted prolate spheroids the values tau 1, 1.08, and tau 2, 1.1. This is when the angle which forms with the major axis of the red blood cell is equals to 0, and the strength of the magnetic field is 9.4 Tesla. We draw this line. Okay, we wanted to see if this is an accurate result, and therefore we proceed in order to draw magnetic lines with taking into account more terms of the series expansion. In the middle, you can see the figure that came up with 2 terms of the series expansion, and then third, the 3 terms of the series expansion. You can see that in our case, the 1 term doesn't came up with good results, but when we use 2 terms of the series expansion or 3 terms of the series expansion, the results are more similar. This is these are the magnetic lines when the angle which forms with the major axis of the red blood cell is equals to pi over 4, and in this case with pi over 2. Let's go to some conclusions. Before our work with Professor Hadjinicolaou, all the models that have been developed for the RBC, red blood cell in the magnetic field, came up with the result that we have homogeneity inside the red blood cell. we see in this figure that inside the red blood cell, which is the blue and the red color, there's no homogeneity, which is normal because of the expansion that we found for the functions phi2 and phi3, which is the sqrt of the square root of tau square plus z square minus 1, which multiplied by a function of three variables tau, zeta, and phi. And we have homogeneity whenever the gradient of the potential is a constant value. We also saw that the geometry affects the homogeneity of the magnetic fields. We believe that this is due to the non-convex domain. And the rotation of the field does not affect the homogeneity of our magnetic field. When we study a problem, it's always arising more problems that we need to investigate and solve. One of them is to see if we can model the red blood cell as a four-layer structure, since the fluid domain stands as it is, but let me show you the same next figure. But the membrane consists of three layers, and therefore this could be a logical extension of our model. We would like to investigate the rate of the convergence of the series of the solution in both cases. We would like to investigate the homogeneity of the magnetic field inside the non-convex particle. As I mentioned before, we believe the non-convex makes the non-homogeneity. And since we use the model with inverted prolate spheroids, which are confocal, it would be a nice extension to model the red blood cell as using similar inverted prolate spheroids. I show the structure of the red blood cell membrane. Some references. Thank you very much for your attention.
Very much for that.
I don't hear very well. I don't hear you very well. Okay. Yes. Yes. You can simply change the variable. The variable tau1 and tau2 are expressing the surface of the red blood cell, the surface of the membrane. If you choose these variables appropriate, you can have every transformation you want. The crucial here is that the shape that we use, the inverted prolate spheroid, is the closer to the original shape of the red blood cell.
Αυτό εδώ.
Το παράδειγμα. Αυτό.
To our next speaker.
University of Patras.
Patras?
Yes.
Perfect.
Hello all, I'm Dr. Bakalis. Along with my colleagues, Professor Vatheas and Professor Papadopoulos, we prepared this work. As an introduction, it has to do with the study of the heat transfer of a laminar ferrofluid flow inside a curved annular duct. We assume that we have a constant transverse magnetic field and a constant temperature difference between the walls. The numerical solution is performed by an in-house code that has been developed in previous works by Papadopoulos and all, using a non-uniform grid. This code has also been validated for ferrofluid hydrodynamic flows, and it involves a general theoretical model for the magnetohydrodynamic flow of micropolar magnetic fluids. Here we can see the geometry of the flow. We have a curved annular duct. Our flow is between the two walls. We assume that the duct length is long enough in order to have a fully developed flow. The transverse magnetic field is vertical to the cross-section of the duct. And regarding the boundary conditions, we assume that we have no slip conditions at the walls and that the dimensionless temperature of the inner wall is 0 and of the outer wall is equal to 1. Just a short description of the mathematical modeling. We have a coupling of the following equations, which are solved using a toroidal poloidal coordinate system. We have here we see the dimensionless forms of the continuity equation, of the momentum equation that also includes the effect of the Lorentz force due to the magnetic field and the effect of the buoyancy forces due to the temperature profile that is induced from the temperature difference between the walls. We have the energy equation, we have the Maxwell equations, and we also have the analytic form of the magnetization equation, which is used to calculate the effect of the magnetic field. We have the following dimensionless parameters: the Reynolds number, the Grashof number, and the Prandtl number. Regarding the Prandtl number, it depends from the concentration of the magnetic particles. When this concentration is 0, Prandtl number is equal with the value of the water, 6.8. As the concentration of the magnetic particle increases, Prandtl number slightly decreases. Regarding the computational method that is used in order to have our solution, we use the CVP numerical variational method. It's a finite difference method that begins with an initial guess of the velocity parabolic profile, assuming an initial guess that we have a parabolic profile. For each time step, we calculate from the following equations the new values for the axial velocity and for the transverse components of the velocity. The Lorentz force effect is calculated by finding the value of m from the analytic expression of the magnetization equation. As the next step, because these values do not quantify the continuation equation, then we have to find the corrections in order for the continuity equation to be valid. So we go to the next step. We find the corrections regarding the temperatures, delta V, and regarding the pressures, delta P. These corrections are then added to the initial estimation of the velocity, and this iteration continues until we have the convergence condition that we can see on the end of the presentation. So, in order to be able to calculate the the effect of the magnetic field, we need to have non-uniform masses that are denser near the walls. This is because the velocity near the walls, due to the effect of the magnetic field, increases rapidly. So there we need to have a denser grid in order to properly to properly address this rapid increase. Here we see a detail of this grid where it is much denser near the walls, near the inner and the outer wall. And this is the equation that we used in order to transform the uniform to the non-uniform grid. We performed the grid independence analysis in order to find the proper size for the grid. We found out that the 40 x80 grid was enough and had a very good accuracy for our case. Here are some profiles for the axial velocity in two different positions. And we see these profiles for a specific magnetic field strength for Xi equal to 0.2, for a specific curvature of the curved duct equal to 0.1, and for a Grashof number equal to 10 in the third. So we have different cases depending on the concentration of the magnetic particles for different values of phi. As we can see on the left plot, where we have the axial velocity profiles at the angle equal to 0, which is the top position of the annular duct, we can see that as the magnetic field increases, it basically suppresses the axial velocity with phi equal to 0 is the simple parabolic hydrodynamic profile, and as the concentration of the magnetic field increases, the effect of the concentration of the magnetic particle increases. Due to the effect of the magnetic field, the axial velocity is suppressed and its top position is moved to the outer wall. On the other hand, at the angle which is equal to 90 degrees, as the magnetic field increases, we also have a suppression of the velocity profile, but the maximum value of the axial velocity is shifted near the inner wall. Here we have some 3D plots of the axial velocity for two different curvatures for a specific value of the strength of the magnetic field and for for a small concentration of magnetic particles. As we can see, due to the curvature of the duct, the axial velocity is shifted at the left side, which is the outer wall of the curved duct. This is due to the centrifugal forces. So for small concentrations of the magnetic field, we can see that the curvature has an effect on the distribution of the axial velocity profile. As the strength field increases, even with low concentration of the magnetic field, we see that the effect of the magnetic field is now significant to the axial velocity profile. 4 poles are distributed with their maximum value to be on the left side and their minimum value to be on the right side. In this case, the curvature, the effect of the curvature, as we can see, it is that as the curvature increases kappa with kappa 0.2 on the left side, the maximum value of the axial velocity also increases on the left side and decreases on the right side in comparison to the plot that we have on the right side. Regarding the transverse components of the velocities, here we can see the effect of the magnetic field on the streamlines. For c equal to 0, we basically have the streamlines of the hydrodynamic case. These streamlines are induced due to the curvature of the duct. In this case, we have a small concentration of magnetic fields. As we can see, as the magnetic field strength increases, and we have also two cases, one without buoyancy forces on the top and one with buoyancy forces on the bottom. As the magnetic field increases, it redistributes the streamlines and it also increases their absolute values, especially for the right case where the strength of the magnetic field is equal to 1. If we increase the concentration of the magnetic particles, we see that in this case the effect of the buoyancy force is suppressed by the magnetic field, because even for small, on the left we have the hydrodynamic case for Grashof number equal to 0 and Grashof number and when we have buoyancy forces, and on the middle and right cases we have increased strength of magnetic field. As we can see, as we increase the magnetic field, the top and bottom graphs are similar, so we understand that the effect of Grashof number in this case has been suppressed by the effect of the magnetic field. Here we have the contours for the temperature, as our main goal on this work was to identify the effect of the magnetic field on the heat transfer between the two walls of the annular duct. We see that in comparison to the simple hydrodynamic profile, the effect of the magnetic field is to reallocate the temperature profiles. This is because it induces a higher value of on the transverse components of the velocity, while in case of c equal to 0, the transverse components of the velocity, the streamlines, were very small and didn't affect the temperature profile. The most important parameter in our case is the average Nusselt number for the inner at the outer wall, which represents the heat transfer between on the walls. Here we have the Nusselt numbers on the inner and the outer wall for two different magnetic particle concentrations, and we see their effect as the magnetic field strength increases. As we can see, especially on the left graph, the effect of the magnetic field and the concentration of the magnetic particles is significant and can help improving the heat transfer on ferrofluid floats inside annular ducts. This is an important conclusion as it can be proven that ferrofluid flows can have a positive effect on heat transfer applications, and this was our main objective. Here are some similar graphs that we have that for a specific curvature and a specific Grashof number, we also check the effect of the concentration of the magnetic particles on the heat transfer. Similar with the previous graphs, we see that also the concentration of the magnetic particles has a positive effect on the heat transfer inside the annular duct, and the combination of the magnetic particles and the increase of the magnetic field can have a positive effect on the total heat transfer. As a conclusion, the velocity distribution, heat transfer, and pressure drop of the ferrofluid flow have been found to be highly affected by the external magnetic field and the concentration of the magnetic particles. The axial flow, especially at high magnetic fields and high concentrations of the magnetic particles, is redistributed in 4 symmetric poles where its maximum value is observed there. As the field strength increases, it basically suppresses the effect of the curvature, so the effect of the curvature becomes negligible and the magnetic field dominates, the magnetic field effect dominates, and the secondary flow that is generated due to the effect of the magnetic field significantly improves the heat transfer between the walls and the fluid. Thank you. No, they have been considered negligible. Also, the Joule heating is considered negligible, and practically are negligible because in this application, what dominates is the heat from the walls and not the heat transfer inside the fluid. Yes. Yeah, basically what we are looking for as future research is to examine additional Reynolds numbers. Due to the complexity of the model and the many parameters that we had to examine, this work is for small Reynolds numbers, up to 100. We would also like to see the effect of the model on higher velocity speeds, higher Reynolds number, and maybe on some turbulent models. Yes. You're welcome. Thank you.
Okay. Hello, good evening. My name is Dimitrios Lambropoulos. I'm a postdoctoral researcher at the Hellenic Open University in Patras. And today I'm going to present you one portion of our work with Professor Maria Hadjinicolaou, entitled Investigating the Impact of Vessel Geometry on Cerebral Aneurysm Formation using Multi-Phase Blood Flow Models. I will try, I know I'm the last person before the lunch break, so I'll try to be as efficient as possible. And I will try to give you a brief explanation and to focus more on the application and not as much on the mathematical equations. So, first of all, what is a cerebral aneurysm? A cerebral aneurysm in general are pathological localized dilatation in the cerebrovascular wall in direct communication with the lumen and therefore the blood flow. The mechanisms driving the genesis and unfortunately rupture of aneurysms remain an active area of research and thus represent a persistent challenge within the scientific community. So, in simple terms, a cerebral aneurysm is a localized pathogenic of the arterial wall, which follows to the formation of a small bulb, as we can see here in the picture. Some stats about the epidemiology of the disease. Unfortunately, evidence suggests that 2 to 6% of the general populations may carry a cerebral aneurysm. Also, unfortunately, the clinical outcome of ruptured aneurysm is abysmal, with 30-day mortality close to 50%. Of those who survive, 25% of the patients suffer severe disabilities, and the rest are at an increased risk for stroke, recurrent bleeding, and other complications. It is not possible or safe to preventively eliminate all ruptured cerebral aneurysms due to associated risks. And also at this point, I would like to add that patients who carry cerebral aneurysms don't know it before. So they go to the hospital having all the symptoms, and unfortunately, when they go to the hospital, is already too late because the cerebral aneurysm has already burst. So it's a bit unfortunate also. So most frequent locations where a cerebral aneurysm is forming. Cerebral aneurysms are most often located at the arterial bifurcations at the circle of Willis. So the majority of them, up to 30%, it's located at the anterior circulation. 25% of them are located at the junction of the internal carotid artery and the posterior communicated artery. 20% of them is located in the middle cerebral artery bifurcation, and just 5.5% is located at the internal carotid artery bifurcation. So there are few ways to classify cerebral aneurysms. The most common one is to classify them according to their morphology. So first and most commonly we have the circular aneurysms, followed by the fusiform, and the least common one, the dissecting aneurysm. Also, they are classified by their size. Clinicians or doctors, when they talk about size, they mean the maximum diameter of the dome of the cerebral aneurysm. So a small aneurysm is considered one that has a maximum diameter smaller than 10 millimeters. A large one is between 10 to 25 millimeters, and a giant one has a diameter of greater than 25 millimeters. Now let's talk about the simulation models. Actually, what is a simulation model? So, and what they do. So actually, simulation models try to represent systems through mathematical expressions and interconnections, offering a deep operational insight. Simulation models mimic real-world system functionality, aiding in comprehensive understanding of system dynamics. Why are they important? Because in our case, when we talk about cerebral aneurysm, in vivo measurements of hemodynamic parameters is complex and risky. Computational techniques such as computational fluid dynamics or CFD present a preferred alternative because, as you may can understand, it is very dangerous and unnecessary to go and measure, let's say, the blood pressure in a healthy person. It's way too risky. So, towards today, CFD is a research tool, unfortunately. shows promise in guiding clinical decision, but it's still a research tool and it has not been yet fully followed by clinicians. Doctors and clinicians they are using traditional geometric parameters such as aneurysm size, which do not always predict rupture risk. For example, aneurysm size, typically using the 7 mm threshold proposed by a paper published in The Lancet in the early 2000s, is currently the most used indicator for treatment. So, as you can understand, no physics are taken into account. However, small aneurysms, often under 7 mm, account for a significant proportion of ruptures. Thus, hemodynamic parameters derived from tools like CFD could help discern which aneurysms to treat, providing a potential enhancement to clinical decision-making. As I mentioned before, I think you heard the word hemodynamic parameters. So the most common hemodynamic parameter used in cases like the cerebral aneurysm is the wall shear stress. So first of all, what is the wall shear stress? Is the frictional force from the tangential flow of blood in the arterial lumen. Proper endothelial function is regulated and mainly dependent on it. Abnormalities in wall shear stress cause dysfunction or loss of the endothelial layer, which may potentially lead to the formation of cerebral aneurysm or other diseases concerning the arterial wall. So here is a typical CFD workflow for cases that could potentially be used in the clinical reality. First of all, we have the segmented geometry, which has been derived from clinical data, mainly DICOM images that are derived from CT scans or MRI scans. Then we discretize our computational domain. Up to this day, the most commonly used method for CFD simulations is the finite volume method. So we create the volumetric cells and all that stuff. Then we numerically solve our Navier-Stokes equations. And then we obtain our results, which consist of the wall shear stresses or the velocity fields. So the scope of this study. First of all, our study explores the impact of vessel geometry on the formation of cerebral aneurysms, specifically through the use of CFD simulation and with the use of a multi-phase blood flow model. So, the study scopes involve the employment, as I said before, the employment of a multi-phase blood flow model to accurately capture the complex nature of blood behavior, the investigation to the effect of vessel geometry, particularly the vessel curvature, on cerebral aneurysm formation, and last, the utilization of simulation results to understand the conditions that potentially lead to an increased risk of aneurysm formation and evolution. So a few words about the multi-phase model that we used. In this particular study, we used the simplified Euler-Euler approach. The blood was modeled as a two-phase fluid consisting of plasma, which was the fluid carrier, and red blood cells. The RBCs were modeled as a particulate fluid, which had a consistent diameter of 7.5 microns. The fluid particulate simulating the RBCs had also a simplified sphere-like shape. Here are the continuity equation and the momentum equation for the two phases. And as for the plasma phase, so the plasma phase is consisting mainly of water. So the stress tensor for the plasma can be mathematically expressed as follows. And this representation assumes a continuous perspective and characterizes the plasma phase as a uniform Newtonian fluid with specific physical properties. As for the RBC's phase, let's say a few things at first. So the red blood cells constitute approximately 45% of the total volume of blood. The local concentration of RBCs, known as hematocrit, appears to affect the viscosity of blood. And the behavior of RBCs in shear flows was represented by the product of effective viscosity and deformation tensor of the cell. Thus, the effective shear viscosity of RBCs was modeled as a non-Newtonian shear thinning fluid. Also, in our try to make our model a bit more realistic, we also included some drag forces. So the GIDAS-POW model was utilized for handling the interface drag forces between plasma and RBCs. The drag term is mathematically expressed as follows. And then we go to the modeling and the boundary conditions that we used for our models. First of all, let me say that all the computational simulation models were developed in the commercial software ANSYS CFX. ANSYS CFX is based on the finite volume method. As an input boundary condition, we used real blood flow waveforms from healthy patients, and we simulated the full 4 cardiac cycles aiming for maximum accuracy. And here is the waveform that our boundary conditions were derived from. Then, the geometry that we modeled. Our goals was to scrutinize the correlation between vessel geometry cerebral aneurysms and the influence of vessel curvature on blood flow and hemodynamic forces. Thus, we established prototype parent vessel geometries that match the dimensions and the shape of the actual cerebral arteries, as you can see in the picture at your right. Our simulations focused on modeling the torus geometry angle and a critical parameter in the vessel curvature. So we systematically altered the prototype's artery angle from 90 to 170 degrees, investigating inch impact of the flow characteristics and blood rheology within the system. Here are the prototype parent arteries that we created. Here is a 2D representation. However, our geometry and models were all on 3 dimensions. And when we're talking about CFD and finite volumes method, consequently, we're going to talk about computational mesh. So a mesh independence analysis was also performed by reducing the mesh size of the prototype geometry. Since the prototype geometries did not differ as much, we conducted the analysis only on the 90-degree geometry. The volume average velocity was used as an indicator for the analysis, and all the meshes are unstructured, employing a combination of tetrahedral cells for the central core and prism cells for the area close to the wall. So here I'm going to present you some of our results. So first of all, we're going to start with the prototype arteries. So our objective was to decipher the intricate link between the arterial curvatures and blood flow patterns. The data collection was strategically performed during the peak systolic of the last cardiac cycle, a crucial phase marked by the maximum ventricular concentration. So this approach provided unique insights into the vascular hemodynamics under high-pressure conditions, aiding further on our understanding of cerebrovascular health. So here is the first bunch of our results. Here are the velocity fields of plasma and red blood cells on the idealized healthy prototype geometry. First for an angle of 90 degrees, 110 degrees, 130, 150, and last 170 degrees. Unfortunately, you cannot see it very clearly in this picture, but after the bend, after the curve, there was a formation of a small recirculation inside the geometry. Here is the red blood cells volume fraction, again on the idealized healthy prototype artery. As we can see, after the bend, we have the formation of a higher concentration of red blood cells in the upper part of the artery. Also, here we have the wall shear stress, which, if I go back to the previous slide, as you can see, the two distributions look alike because, as we saw before, the red blood cells were kind of trapped in the upper part of the artery, so as it is natural, the wall shear stress caused by the actual red blood cells is higher on the place that they are trapped due to the flow conditions inside the artery. And here is the volume fraction gradient. The volume fraction gradient shows how much the volume fraction of the particular phase is changing in a certain part of our geometry. So here we can see again that at the same part of the artery where the RBCs were trapped, we have the maximum volume fraction gradient. Then we move to the prototype arteries with circular aneurysms. So using previous insights, simulated 8 mm aneurysm is constructed where the jet stream of the plasma and red blood cells impacts the vessel wall. The aneurysm aligns with the hemodynamic stress point, allowing a detailed study of its behavior under these conditions. The focus will be, at this point, will be primarily on the RBC's behavior, and our goal is to understand the RBC's behavior under various conditions, as is the key to studying aneurysm dynamics, given the central role in aneurysm formation and evolution. So here again, we present, as you can see in this photo, there are the prototype pensient arteries this time because they carry also the cerebral aneurysm. So we are talking about prototype geometry, so the aneurysm has a simple sphere-like shape again. So here is the volume fraction, and what is very interesting is that we see that inside the aneurysm, the volume fraction of the red blood cells is actually, has actually a high value, which means that a great number of red blood cells is trapped inside the aneurysm itself. Here is also the volume fraction gradient, which supports the previous finding. It supports the finding that the red blood cells are trapped inside the aneurysm. So the volume fraction gradient here is close to 0, which means that there is no particular change in the volume fraction inside the dome of the aneurysm. Also, that comes also into play. What comes also into place is the low wall shear stress that we can see here in this picture. That inside the aneurysmal dome, the wall shear stress is quite low. And at this point, I have to mention that low wall shear stresses are very much linked with the evolution of cerebral aneurysms. So in simple terms, when we come to low wall shear stress inside the cerebral aneurysm, that means that is a bad indicator that our aneurysm will develop and at some point will burst. So, our conclusion. So, the multi-phase blood flow model, in contrast to the traditional single-phase models, Newtonian or non-Newtonian, provides a better understanding of blood component dynamics, especially the behavior of red blood cells within the aneurysmal dome. The curvature of the prototype parent artery significantly influences the plasma and the RBC's distribution patterns and consequently the wall shear stress values. Our research emphasizes the importance of local hemodynamics alteration in aneurysm pathogenesis and suggests that geometric peculiarities in cerebral vasculature, such as curvature, are potential stressors leading to aneurysm formation. And last, while this research adds valuable insights into the complex dynamics of cerebral aneurysms, it also reinforces the need for further research using sophisticated modeling techniques to fully understand these life-threatening conditions. And before closing this presentation, I would like to dedicate this whole work to Professor Fotini Kariotou. Unfortunately, Professor Fotini Kariotou passed away tragically 2 weeks ago. A few words about her. She was one of the kindest and most noble persons that I've ever met. Unfortunately, I knew her only 2 years, so yes, I would like to. I'm sure that she could be here. She will be here, and she would be proud of us, and she would be proud of this work because she was heavily involved in this work in the first steps that we made. So unfortunately, she's not with us anymore. Thank you. Thank you very much. Yep. Okay, nice question. So, first of all, the hypothesis of a two-phase model is quite important because we can model how the actual blood is, because blood is not a single-phase fluid. So if we address that, yes, it's important also for the formation of an aneurysm, and also if you already have an aneurysm, it's important to know how this aneurysm will evolve. So it's important for both of your questions. Yeah, we want to know when it's going to form, and if it's already there, we want to know how it's going to evolve. Yes. We will also consider a three-phase blood flow model with the white blood cells also included. That will be our next steps. And also, I will try to incorporate a more advanced model that takes into account the peculiar shape of the actual shape of the red blood cell model. But that would be on a future. Yes. No. Unfortunately, the software that we used for this whole simulation model was commercial, so we got only what the software allows. Yeah. So what the software allows was the drag force. That's what we had. That was included in our analysis. If you want to go a step further, you have to do it on an in-house code. Code everything by yourself, which is our next goal. This was our initial endeavor to show how these things work. Thank you. Thank you very much.
All. Ναι. Α, ναι, βέβαια.
Ξεχάσα να βγάλω φωτογραφία. Εντάξει, ευχαριστώ.
Marilena, should I put my talk? Bien. This is for you. You will see. I am going to compose 2 backward stable things, and at the end there will be a mess. 40 minutos, empieza a las 3 y termina...
O sea, la duración de una siestita, ¿no?
¿Lo pongo ya? Sí.
So, good afternoon. Now we're going to listen to our colleague Froilando Pico. We'll be talking about backward stability in polynomial and rational eigenvalue problems.
Thank you very much, Mustafa. And in the first place, I would like to thank the organizers. I am really very happy to be here. I'm very honored and to meet many good friends that we have not met in the last years. I am going to talk about a number of results that I have obtained in the last 5 years with several people, Piers Lawrence, Javier Perez, who used to be a PhD student of mine, but now is in the University of Montana, Maria Quintana, that was another PhD student of mine, and now is in Aalto in Finland, and Paul Van Doren from the University of Leuven. Okay, let me start with a very informal introduction. From a very simplified and non-rigorous point of view, we can consider the following matrix eigenvalue problems. We have first the basic eigenvalue problem, that is the one that all of us know. We have a constant matrix, and we want to compute its eigenvalues and its eigenvectors. We have the eigenvalue-eigenvector equation that I write in this yellow form. Then we have the generalized eigenvalue problem where we have two matrices. In fact, these matrices can be rectangular, and we want to compute again some numbers, eigenvalues, and some non-zero vectors that satisfy these eigenvalue-eigenvector equations. Often, but not always, under the regularity assumption that the determinant of set B minus I is not identically equal to 0. That means that the problem is regular. We can generalize this if instead of two matrices we have D plus 1 matrices, in this case P0, P1 up to PD, we can consider the polynomial eigenvalue problem that you see here, and again we want to compute scalars that are the eigenvalues and non-zero vectors that satisfy this equation, often, but not always, under the regularity assumption that the determinant of the matrix polynomial that you see there is not identically 0. I am not going to assume regularity along my talk, but usually the most important problems nowadays are regular problems. But I will not assume regularity. And finally in this talk, but not finally for the eigenvalue problems, we have rational eigenvalue problems, where we have something that is called a rational matrices that can be rectangular, and a rational matrix is a matrix such that each of its entries is a scalar rational function of a scalar variable, and again we want to compute some numbers that are called, let us call it eigenvalues, In the rational problems, they are called more rigorously zeros, and some non-zero eigenvectors that satisfies this eigenvalue-eigenvector equation, again, under the regularity assumption that the determinant is not identically zero. We focus in this talk on polynomial and rational eigenvalue problems. I want to emphasize that polynomial and rational eigenvalue problems are important by themselves. They appear in many applications, but in addition, they are very important because in the last years, they have been used as approximations of more general nonlinear eigenvalue problems. But I am not going to talk about more general eigenvalue problems. I will focus on polynomial and rational eigenvalue problems. A key idea in eigenvalue problems, in matrix eigenvalue problems, is the following. Polynomials and rational eigenvalue problems can be solved by transforming the problem into a generalized eigenvalue problem via a process that is known linearization. I want to emphasize that this transformation is exact, in the sense that the obtained generalized eigenvalue problem contains exactly all the eigeninformation of the original polynomial eigenvalue problem or rational eigenvalue problem. Please do not think that linearization means an approximation, that I am discarding some kind of higher order terms. It's an exact transformation that transforms a polynomial eigenvalue problem or a rational eigenvalue problem into a generalized eigenvalue problem. Okay? The use of linearizations, in fact, is one of the most reliable approaches for solving numerically polynomial and rational eigenvalue problems because there exist very reliable algorithms for solving the generalized eigenvalue problem. Okay, this lambda b minus a times b equal to 0, this is the generalized eigenvalue problem. We have very good algorithms for solving this problem, and then we can solve polynomial and rational eigenvalue problems via linearizations. This approach is not new, it's very classical and has been studied by many researchers in the last 2 decades. What is the goal of this talk? We will study the backward stability of solving polynomial or rational, of solving a polynomial or a rational eigenvalue problem by applying a backward stable generalized algorithm to a wide family of its linearizations. At this moment, you can think, okay, we are done, because we have transformed our problem exactly into a generalized eigenvalue problem. We apply a backward stable algorithm to the generalized eigenvalue problem, then we have got backward stability. But we will see that this backward stability problem is not trivial, because the linearizations are highly structured pencils, and the backward errors of the generalized eigenvalue algorithm destroys such structures. We will see this during the talk. Okay, this is the outline of the talk, and I am going to start with a brief reminder of what is the eigenstructure of a polynomial and a rational eigenvalue problem, and I will describe the rest of the points as we advance in the talk. These are our problems, and then so far we have only considered very informally something that is called finite eigenvalues. But generalized eigenvalue problems, polynomial eigenvalue problems, and rational eigenvalue problems may have also infinite eigenvalues that in computations are somewhat annoying. In addition, when they are singular, this means when they are rectangular or square with identically zero determinant, these eigenvalue problems have, in addition to eigenvalues, other numbers that are interesting that are called the minimal indices. And finally, rational eigenvalue problems have poles. I am going to define very quickly these concepts. Given a matrix polynomial that may be rectangular or singular, lambda naught is a finite eigenvalue of the polynomial if the rank of the matrix that we obtain when we evaluate the polynomial in lambda naught is strictly less than the maximum possible rank when we evaluate the polynomial in every complex number. This is the definition of a finite eigenvalue, and the infinite eigenvalue is usually defined through the reversal polynomial. What is the reversal polynomial? The reversal polynomial is a polynomial in which we reverse the order of the coefficients. In the first in the polynomial in the first line, the first coefficient is PD, the last one is P naught, and in the reversal polynomial, the other way around. The first coefficient is P naught, and the last one is PD. And then we say that matrix polynomials have an infinite eigenvalue if the reverse polynomial has a 0 eigenvalue, and the multiplicities are defined correspondingly. What about the minimal indices? Well, the minimal indices, when a polynomial is singular, rectangular, or square with a determinant that is identically equal to 0, well, just to mention that these polynomials do not appear perhaps so often in applications, but they do appear, for instance, in system theory and control theory. These polynomials have other numbers that are called the minimal indices. The definition is not so simple. Let me give the definition, but really you don't need to know exactly what are these minimal indices. Simply to understand that there are other numbers in addition to the eigenvalues in these problems. The definition is done in the following way. When a polynomial is, a matrix polynomial is singular, it has non-trivial left and right null spaces when we consider the polynomial as a matrix over the field of rational functions. Then we have left and right null spaces. Now the vectors in these null spaces, the entries are rational functions or polynomials, and it is clear that these subspaces have bases consisting entirely of vector polynomials. And among these bases consisting entirely of vector polynomials, there are some of them that are minimal in the sense that the sum of the degrees of their vectors is minimal. These are called the minimal bases of the polynomial. We have left minimal bases, right minimal bases. There are infinitely many of them. But the key point is that the degrees of the vector polynomials in any minimal basis is always the same. And these numbers are called the minimal indices of the polynomial. Then, as a summary, the complete eigenstructure of a polynomial matrix is comprised of its finite eigenvalues with their partial multiplicities, its infinite eigenvalue with its partial multiplicities, its right minimal indices, and its left minimal indices. We have 4 components of the eigenstructure. I have not defined partial multiplicities. Rigorously, they are defined through the Smith 4. In the case of matrices or pencils, they are just the sizes of the Jordan blocks associated to each eigenvalue. And I am not going to introduce the definition of the eigenstructure of a rational matrix, but let us say simply that in addition to all the eigenstructure of a polynomial matrix, we have poles, finite zeros, finite poles, infinite zeros, infinite poles with partial multiplicities that are defined through theoretically with something that is called the Smith-Macmillan 4. And the infinite zeros and poles of the rational matrix corresponds to the zeros and poles at 0 of the rational matrix that we obtain with the change of variable lambda goes to 1 over lambda. This is the complete eigenstructure of a rational matrix. Then let us move to what are linearizations of polynomial and rational matrices. Okay, this is the definition that does not say too much at the beginning. A linear polynomial matrix of a matrix pencil is a linearization of a matrix polynomial if there exist unimodular polynomial matrices. Unimodular polynomial matrices are matrix polynomials whose they are square and the determinant is different from 0 and is constant. That satisfies this equation. The linearization is unimodularly equivalent to the direct sum of the identity and the polynomial. In addition, if in addition the reversal of the linearization is a linearization for the reversal of the polynomial, we say that the linearization is a strong linearization. This is the definition, but the important thing of this definition is that it guarantees the following. A matrix pencil linear matrix polynomial is a linearization of a polynomial matrix if and only if L and P have the same number of right minimal indices, the same number of left minimal indices, the same finite eigenvalues with the same partial multiplicities, and L is a strong linearization if and only if, in addition to 1, 2, and 3, L and P have the same infinite eigenvalues with the same partial multiplicities. This is what is important for us. A linearization preserves these quantities. I observe that the minimal indices of the linearization may be arbitrarily different from those of the polynomial. The definition only guarantees that they have the same number of right and left minimal indices, but in the most important classes of linearizations, they are easily related. What is the most famous linearization? The Frobenius companion form. If we have a matrix polynomial, we construct this pencil. Observe that this pencil has a lot of structure. We construct this pencil with the coefficients of the polynomial, with blocks that are equal to the identity and lambda to the identity, and the rest are zero blocks. And I want to emphasize, I am not going to explain exactly the result, is that this linearization is one of these linearizations whose minimal indices are very easily related to the minimal indices of the polynomial. They allow us to recover the minimal indices of the polynomial. Good. What about linearizations of rational matrices? I am not going to present the formal definition, also because there is no agreement in the community on how to define a strong linearization of rational matrices. There are pioneering works in the 70s and 80s by Van Doren and Verghese about linearizations of rational matrices, though they did not give a general definition. With my colleagues Amparan, Marcaida, and Zavalla, I introduced a definition of a strong linearization with the nice property that it reduces to the definition of polynomial matrices when the rational matrix is a polynomial, and we constructed explicitly many of such linearizations. Other authors, Alan and Behera, have introduced other definitions that are more or less equivalent. But for this talk, in simple words, a linearization of a rational matrix is a matrix pencil, matrix polynomial of degree 1, whose eigenvalues are the finite zeros of the rational matrix, and such that the eigenvalues of a certain square and non-singular submatrix of L are the finite poles of the rational matrix, with equal partial multiplicities for the zeros and the poles. When L contains also the pole and zero information of R at infinity, then we say that it's a strong linearization. There are many families of strong linearizations of polynomial and rational matrices, and the family that I am going to consider in this talk includes modulo permutations, many of the linearizations that are available in the literature. Not all, but many of them. Let us introduce the family of the linearizations I am interested in this talk. They are called Bloch-Kronecker linearizations of polynomial matrices. And in order to define, we need these auxiliary polynomial matrices, LK, that is a rectangular polynomial matrix by diagonal, -1s in the first diagonal, lambdas in the first superdiagonal, and it has one more columns than rows. And also I will use the vector of the monomials, capital lambda K. Okay, the vector of the monomials, and I am going to use in the definitions really the Kronecker products of these polynomial matrices times the identity. I want to emphasize that we have seen these matrices before. Let us go back to the Frobenius companion form, highly structured pencil, and observe that if we ignore the first block row, we get a block by diagonal matrices minus identities, lambda identities in the diagonals, and this can be written in this compact form using the previous definition, the previous auxiliary matrix that we have introduced. And now, if we pay attention to the first block row, and we multiply the first block row by the vector of monomials, Kronecker product with the identity, we get the polynomial. Okay, in the Frobenius companion 4, we have these auxiliary matrices, and now we are going to generalize the Frobenius companion 4 to something that is called a block-Kronecker pencil. A block-Kronecker pencil is a pencil with this structure. In the off-diagonal, we have these bidiagonal matrices. In the 1-1 block, we have an arbitrary pencil, and then the key point is that any block-Kronecker pencil is a strong linearization of the polynomial matrix that we obtain multiplying M, what the linear pencil in the 1-1 block, but these monomial matrices on the left and on the right. And in addition, we can recover via addition the minimal indices of the linearization from those of the polynomial, just summing this epsilon and eta. These are the block-Kronecker linearizations. The Frobenius companion linearization is the example that motivates is a block-Kronecker linearization. But there are many other block-Kronecker linearizations. This is one, for instance. This has been important in application because this is symmetric when the polynomial is symmetric, or Hermitian when the polynomial is symmetric. But we have many other of these linearizations. Block-Kronecker linearizations of rational matrices. We need to introduce a few more auxiliary. Well, first, something important I was forgetting. Rational matrices can be represented in different forms. And this is important because in this talk and in my analysis, I am assuming that the rational matrix is expressed in this way, as a sum of a polynomial matrix, and then we have this that represents what is called the strictly proper part of the rational matrix, the part of the rational matrix that goes to 0 when lambda goes to infinity. And we assume in addition that A, B, and C is a minimal state space realization. This is the definition of this meaning of minimality. Probably many of you know this concept of minimality. But the important thing of the minimality is that when we have minimality, the eigenvalues of A are the poles of the rational matrix. If we don't have minimality, this is no longer true. But when we have minimality, the eigenvalues of this matrix A are the poles of the rational matrix. I want to emphasize that any rational matrix can be represented in this form, and this form is one of the most standard representations in linear systems theory. But if you have a rational matrix and it's not represented in this form, and you insist in representing the rational matrix in this form, you can make errors. I am assuming that we have the matrix in this form, and then we do not commit any errors for getting this representation. There are many important examples of modern examples of rational matrices that can be represented in this form. These are just a few of them. But I want to emphasize these are recent examples that can be represented in this form, but there are also very important examples, recent examples that have been very important in the development of algorithms for rational eigenvalue problems and nonlinear eigenvalue problems that cannot be represented in this form, okay? Then this is always possible, but some of them are not represented in this form, and to get the representation necessarily would imply some errors in the computation. Okay, good. In order to define the block-Kronecker linearizations of rational matrices, we need some auxiliary matrices. We have already seen these two matrices, the bidiagonal matrix of 1 and minus lambda, the monomial basis, the monomial vector with all the monomials up to degree k. In order the block-Kronecker linearizations of rational matrices are more complicated, then I am going to use this compact notation for these Kronecker products of the bidiagonal matrix times the identity. And I am going to introduce these matrices that are block matrices of zeros and one identity at the end of proper dimensions, okay? Block matrices of zeros and identities. And with this, I can introduce this pencil. Observe that this pencil, we have here a block-Kronecker linearization of a polynomial matrix, and here we complete with A, B, and C, and these matrices that have block of zeros and an identity at the end. And it is possible to prove that if A, B, and C are minimal in the sense that we have explained before, then these pencils that are the Bloch-Kronecker pencils of this rational matrix are a strong linearization of this rational matrix. This is the strictly proper part, and this is the polynomial part. Okay? I want to emphasize that I am expressing this in this way, but in the analysis I am going to permute. I am going to permute or many times they appear permute. I mean that not always you see the Bloch-Kronecker linearization of a rational matrix written in this way. Some other times it is written in this other way with other permutations of the blocks. Good. There are many examples of this Bloch-Kronecker linearization. This is an old one. Again, a very highly structured pencil. This is a more recent one used by Su and Bai very recently for compute eigenvalues of rational matrices. And there are infinitely many of these representations. This is one that can be made symmetric if the rational matrix is symmetric. Always we have highly structured pencils with the coefficients of the polynomial pair, A, B, and C, a lot of block of zeros and identities. Good. Then let us go to the problem. Global backward stability of polynomial eigenvalue problems solved with linearizations. We are given a general polynomial matrix, and we assume that it's complete eigenstructure. If you prefer and you are not familiar with singular polynomials, assume that we have computed just the eigenvalues. Applying a backward stable algorithm to one of for instance, backward stable algorithm for regular polynomials, the well-known Q-set algorithm that is implemented in MATLAB. We have applied this to a strong linearization in the class of Bloch-Kronecker linearizations of P. What does this mean? This means that the computed complete eigenstructure of the linearization is the exact complete eigenstructure of a perturbed pencil, such that the norm of the perturbation over the norm of the linearization is ordered unit round off. This is the meaning of backward stability. Okay, here I am using the Frobenius norm of a pencil, and I am going to use also the Frobenius norm of a polynomial, and the Frobenius norm of a polynomial is defined as the square root of the sum of the square of the Frobenius norms of the pencil. And then we obtain this here. This is what is guaranteed by the backward stability of the Q-set algorithm, for instance, but the question is the following. Does this imply that the compute complete eigenstructure of the polynomial is the exact complete eigenstructure of a polynomial matrix of the same degree and such that is a small perturbation in this sense with U the unit rounders of the original polynomial? Is this true? The question is not obvious because Bloch-Kronecker linearizations are highly structured pencils and the perturbations destroy the structure. Let's go back to our preferred example, the Frobenius companion 4, and imagine that you perturb this with a pencil. Sorry, I have to go back. Then you get a pencil where you don't see the polynomial. The block of zeros have disappeared. The identities here that are constant now are perturbed also with terms in lambda. Here we don't have terms in lambda, now we have terms in lambda. This is a mess. Apparently we don't see any polynomial there, or it is not clear if we have a polynomial there. Then our first problem is to establish conditions under which, on the size of the perturbation such that L, the original pencil, the original Bloch-Kronecker pencil, plus the perturbed pencil, is a strong linearization of some polynomial matrix of degree D. And then, once we are sure of that, we have to prove a perturbation bound. This here on the right, the quotient of the backward error in the linearization divided by the quotient of by the norm of the linearization is what we know is ordered unit round off. But we want this to be ordered unit round off. And then we have to find the relation between these two quotients. This will be a number depending on the polynomial and the linearization. And for those polynomials and those linearizations such that this number is moderate, to use global backward stable algorithm on the linearization will give global backward stability on the polynomial. Okay, let us see what we have found for this number. What we have been able to prove is that if the perturbation of the Bloch-Kronecker linearization of the polynomial P is small enough, this is the exact meaning of small enough, but simply think that it's small enough, then the original Bloch-Kronecker linearization plus the perturbed linearization is a strong linearization of a polynomial matrix with grade D, and such that we have this relation. The quotient of the perturbation of the norm of the perturbed polynomial divided by the polynomial is the quotient of the perturbed linearization divided by the norm of the linearization multiplied by this thing here, where we have the norm of the linearization, the norm of the polynomial, and the norm of this one block. And here one constant that depends on the degree of the polynomial. Good. What happens with this constant? Well, it can be proved, it's not so easy to see. It can be proved that if the norm of the polynomial is very small or the norm of the polynomial is very large, then this constant is very large. Okay? But recall how is the polynomial eigenvalue problem? Is P lambda V equals to 0. We can multiply the polynomial by a constant and we still have the same eigenvalues and the same eigenvectors. Then we can control this. And the other thing that happens is that if the norm of this is much larger than 1, then this is also larger than 1. Then, for getting backward stability from Bloch-Kronecker linearization, one needs first to normalize the matrix polynomial. To have norm 1 is the ideal thing. This is rather intuitive because for instance, in the Frobenius companion 4, we have the coefficients of the polynomial and then identities. If the coefficients of this polynomial are very large or very small, then if they are very large, they are not going to see under small perturbations the identity. If they are very small, the identities are not going to see under perturbations the polynomial. This is something that we expect. And then we have to use pencils for which the norm of this 1 block is equal to the norm of the polynomial. And if you do these two things, then you have a very nice perturbation bound that guarantees backward stability of the problem of computing the complete eigenstructure of a polynomial using linearizations. This is satisfied by the Frobenius companion 4, of course, for Fiedler linearizations and for many other linearizations that have been used in the literature. Okay, then the last part of the talk is global backward stability of rational eigenvalue problems solved with linearizations. Well, we need some additional norms. We have already used the Frobenius norm of a matrix polynomial, but now we are dealing with rational matrices represented in this way. And we need to measure in some sense this, and we are going to adopt this norm. I know that this norm is not the norm of a rational matrix, that is simply the norm of the polynomial part, and we use the square of the Frobenius norms of A, B, and C, and the Frobenius norm of the identity. For those of you that are familiar with polynomial system matrices, this is not really the norm of the rational matrix, it's the norm of something that is called a polynomial system matrix related to the rational matrix, this matrix. Okay, then I am going to use this norm for measuring the backward errors, and I am going to use also very quickly the two norm of a matrix pencil is going to be, this is going to appear very quickly as the two norm of this matrix in our analysis. Then the problem is more or less the same as in the polynomial. we have a rational matrix represented in this way. We are given this representation, and its zeros, and if you want, its minimal indices are computed by applying a backward stable algorithm, the Q-set algorithm, for instance, for computing the eigenvalues of its Bloch-Kronecker linearizations. These are the Bloch-Kronecker linearizations, where the polynomial part is given in terms of this 1-1 block multiplying by the vectors of monomials. Good. And then this means that we have computed the exact eigenvalues and the exact minimal indices of a pencil, not the pencil S, a perturbed pencil, such that the quotient of the node of the perturbation divided by the node of the pencil is ordered unit round-off. This is what we have computed. And then the question again is, does this imply that we have computed the exact zeros of a nearby rational matrix? Nearby in an structural sense, nearby that we have really perturbed the coefficients that define the problem, the A, B, and C, and the coefficients of the matrix polynomial. We have computed this with this small backward error. Again, why this problem is not easy? Because the perturbation destroys completely the delicate structure of the Bloch-Kronecker linearizations. I am not going to get into the details, but I would like to say that this problem is considerably harder than in the polynomial case. Why is considerably harder? Because I still have 5 minutes, Mustafa. Okay. This problem is considerably harder, and the results are not going to be so nice. Because the corresponding Bloch-Kronecker pencils for rational matrices are more complicated. We have more structure, and we have also more structure than preserved in the rational matrix, and requires some additional tricks and techniques that I am not going to explain. Anyway, we have been able to prove that if we perturb a Bloch-Kronecker pencil of our rational matrices, then the eigenvalues and minimal indices of the perturbed pencil are the zeros and shifted minimal indices of a perturbed rational matrix in this structural sense, perturbing each of the coefficients that defines the rational matrix. And we have this relation between the backward errors in the rational matrix and the backward errors in the linearization that are the ones that I know that are small. And here appears something that is horrible. It's a very complicated structure, constant that depends on the node of the rational matrix, the node of the linearization, and here there are some other constants that you can see here. They are complicated. The only thing is that they only depend on the initial data. Then, when this complicated number is moderate, then we have guaranteed structural backward stability. However, this magnitude can be very large if S, the node of the linearization, is large, or even under the weaker condition that the node of the rational matrix is large. And we have performed numerical experiments that this is true. This analysis assumes a lot of inequalities that are not probably optimal, but we have checked that numerically this is true. Then additional conditions are needed in order to guarantee the structural backward stability. And these are the conditions. We need first that the node of A, B, C, and the node of this polynomial are smaller than or equal to 1. And also, this is a condition on the rational matrix, and this is a condition on the linearization. The n block on the linearization, the node should be equal to the Frobenius node of the polynomial part. This happens for many linearizations. Not for all, but this happens for many linearizations. And then under these two conditions, we have a very nice bound here. Then we have backward stability. But here we have a problem, is that there are rational matrices for which does not happen. And in order to make this happen, we have to scale the original rational matrix. I don't want to get into the details of how to scale the original rational matrix, but I want to emphasize that the things are not so nice as in the polynomial case, because we have to scale also the variable. we have to scale also the variable in order to get this condition. This is because we insist in having this identity here. We can do a different analysis without having the identity here, having here a matrix B, but if we do that, then a matrix B, no, because B is also here, a matrix F. But then if we do this other analysis, in the backward errors appear the condition number of that F. Then things are not so nice as in the polynomial case. And then if, with this scaling, we can get a rational matrix that satisfies the desired conditions. This can be done without any error with the scalings that are integer powers of 2. And I emphasize that this requires to scale also the variable lambda in contrast to the polynomial case. And it's not fully clear what happens when you scale the variable lambda. It depends on what type of backward error you consider, but I am not going to get into this. Then the conclusions are the following. We have proved that the computation of the complete eigenstructure of a matrix polynomial, regular or singular via Bloch-Kronecker linearizations, is backward stable from the polynomial point of view. If the polynomial is multiplied by a number in such a way that the NOR is equal to 1, and the linearization is chosen in such a way that the 1-1 block of the linearization has a NOR equal to the NOR of the polynomial, which happens for many of the linearizations used in the literature. We have obtained similar results for rational matrices expressed in this form, though in this case, a delicate scaling of the rational matrices which requires to scale the variable is needed. And we have also analyzed structured polynomial matrices, Hermitian, with Hermitian coefficients, alternating between Hermitian and skew Hermitian coefficients, palindromic polynomial matrices, with a structure preserving backward errors, and we have obtained similar positive results. And this is all. Thank you very much for your attention.
Do you have questions? Pico?
They don't have questions. Too much backward error analysis.
Understood everything.
There are still activity on finding new linearizations, but I think that we have already many linearizations, probably, but there are still persons and researchers that have problems expressed, especially rational problems expressed in a different way, and then they introduce new classes of linearizations.
Oh, in mind, certain properties.
Yeah. This is interesting. Many people have done research, and they are still doing research. Now, in fact, the last thing that I have seen is linearizations for, they are not the same for matrices whose entries are analytic functions. And then they linearize in a certain way, and they say something is not a linearization in this sense, but there are still activity in the field. What there are not so much activity is on the backward error analysis, that there are still a lot of open problems, probably because it is very messy. And in the rational case, at the end, the results are not as good as we would like. You have to. The key point of the analysis that we have done in the rational case is that you have to precondition the rational matrix before you apply the algorithm. Yeah. This is a backward error analysis. well, the problem with the backward errors is with the forward errors is that the conditioning of the problem is really there, and also take into account that we are solving the linearized problem using a backward stable algorithm. The Q-set algorithm is not forward stable because it's backward stable. It's not forward stable because for ill-conditioned problems you don't get accurate results. Okay. Okay. The bounds, yeah. There is a lot of work. Thank you, Marilena.
Okay, so let's thank again Professor Dopico.
Thank you.
Natasha, please come. Το έχεις αστικάκι εδώ ή θα βάλεις το λάπτοπ? Οκ.
Το βάλω και εδώ πέρα.
Ωραία, βάλεις το εδώ.
Πού το ποτέ. Πού το κάνω μια στιγμούλα. Όχι, δεν μου το φοβάσαι. Users.
Θα μιλήσεις μόνο εσύ, έτσι?
Ναι.
Είσαι έτοιμο?
Τώρα το βάζω εδώ πέρα. Γι' αυτό τα έχουμε βάλει όλα στην GitHub, έτσι ώστε να μπορούμε να το πάρουμε οποτεδήποτε χρειαζόμαστε. Ελπίζω. Το κάνω download, έτσι. Μπορώ να το κάνω download. Θα το κάνω download στο υπολογιστή. Ωραία. Hello. Okay. Good afternoon, ladies and gentlemen. As Ms. Marina Mitrouli said, we are the Julia team from the Department of Mathematics of the National Capodistria University of Athens. Now, the topic of our poster is the Julia programming language. For those that do not know, Julia is a high-level, high-performance, this is really important, it is a high-performance dynamic programming language. It is a pretty young language, and as we can see here, its first stable release dates back in 2018, and since then, it has become even more popular. Now, some of its characteristics are displayed here into this quote, which is from the creators. First of all, it is open source. It is as fast, almost as fast as C. It is optionally typed. It is composable. It is reproducible. And it uses general purpose programming language, meaning that we can actually create any software that we want. But it is specialized for numerical analysis and scientific computing. Now, the content of our poster is, of course, an introduction and a guide to Julia language, meaning that we have functions and methods, constructors, control flow, and if anyone wants to go deeper into the language, we do have grammar syntax, regex, of course, memory management, runtime system, and many more. Of course, we do have interactive applications. When I say interactive, I mean that we are using the Pluto notebooks. Pluto notebooks are like Jupyter notebooks, but the main difference in that the shell executes codes of Julia. Now, the first application that we have is the accuracy of different expressions representing equal quantities. Second one is interactive program that converts numbers from decimal to binary. Another one is interactive program that prints binary rational numbers, meaning numbers that have finite binary representation within a given range. We have benchmarks of algorithms which find whether a number is prime or not. The language that we used for this application is MATLAB, Julia, of course, and Python. Then we have Julia's efficiency in the Newton-Raphson method and matrix computations, benchmarking it against MATLAB, Python, and Julia. And lastly, we have Lagrange and Newton's interpolation, that is all the applications that we have. I would like to thank you for your time, but before ending the presentation, I would like to add that we do have a GitHub organization. The name is NKUA Math-Julia, and specifically for this conference, we do have a repository with the name NASCA 23, where you can find all the notes that we have. And of course, there is an HTML site. We do have a site where we have the static HTML export of all the notebooks. And you can run all the notebooks, the code of it, in your machines. Thank you very much, and we would love to see you during any of the breaks.
Okay. So, as another application of the Julia programming language, what we effectively did is we studied the growth problem of Adamar matrices of order 20. As Ms. Mitrouli said, it is a very important problem in the analysis of the numerical stability of Gaussian elimination. Specifically, the beginning of our inquiry is given an invertible matrix, an invertible square matrix, obviously, of some order. We want to decide, actually, when we apply Gaussian elimination with complete pivoting to it, its pivots and growth factor arise as quantities of interest. The reason behind this is the fact that using the pivots we can calculate the growth factor, and the growth factor appears in the analysis of the numerical stability of Gaussian elimination with complete pivoting. Specifically, if we were able to find a relatively low upper bound for the growth factor of any matrix of order n, such as n or n squared, n is actually known to be impossible generally. It has been proven not to be an upper bound. But if we could find a relatively low upper bound, we could prove that the algorithm, GCP, is in theory and not just in practice stable. In this poster specifically, we're interested in the behavior of these pivots, mostly their absolute values, to be specific, and the possible pivot patterns, which is just the sequence of all pivots, for Hadamard matrices, which are orthogonal matrices comprised of ones and minus ones. Two Hadamard matrices of the same order are considered to be equivalent if we can obtain one from the other by performing a finite sequence of row swaps, column swaps, or row negations and column negations. And basically, for order 20, there are 3 equivalence classes, but that doesn't mean that the problem of finding all the possible pivot patterns is easy for Hadamard matrices of order 20, because equivalent matrices, equivalent Hadamard matrices, do not need to have the same pivot pattern. Therefore, in order to try and find new pivot patterns, we can take a representative from each class, from each equivalence class, and perform operations of the above types and generate a new matrix, which we can then apply GCP on and find its pivot pattern. We did this programmatically using the programming language Julia, which is why this fits with the previous, with the rest of the other poster, basically. So far, what we have found is that after searching exactly 2.5 billion matrices and recording the relevant results, we have found exactly 1,244 pivot patterns, and after a lot of searching, no new ones were found, so it is possible that only these exist, or that some other one exists that may be very rare. It should also be noted that we used rational numbers during this search, because using floating point arithmetic could result in inaccuracies and perhaps confusing 2 different pivot patterns for the same or vice versa. Therefore, we use rational numbers and we know the pivot patterns with absolute precision, and we can also test whether 2 pivot patterns obviously are equal with absolute precision. Based on the generated data, and this is why this problem is, this search is interesting, effectively, there is the conjecture that the growth factor of any Hadamard matrix is equal to its order, and specifically, it is an open problem whether this is an equivalence, that a matrix has growth factor equal to its order if and only if it is an Hadamard matrix. And based on the data we generated, this conjecture, specifically one of the 2 directions, the first I mentioned, appears to be true for n equals 20. Our results also support other results in the literature, such as certain bounds and lists of all the possible values for certain pivots that have appeared in some papers. That's it, basically. Thank you for your time. If you want to know more or if you have any questions, you're welcome to come and see and discuss the poster during any of the coffee breaks. We would love to see you there. Thank you.
moment. Άστο. Πού να το βάλω? Just a moment. Okay. I would like to thank the conference board for the opportunity to present our work. It has to do with the approximation of the spectral radius of non-negative matrices. More specifically, matrices that have non-negative elements. So, we obtained some, first of all, this is the definition of the ith row sum. And in the second bullet, there are two quantities that depends on the row sum, the minimum row sum, denoted by r lambda, and the maximum denoted by r nu. Using these quantities, we managed to obtain some, we also denote and define z and omega, and we managed to obtain some bounds for the spectral radius of a non-negative matrix that somehow generalize the well-known result by Frobenius, stating that the spectral radius is bounded by the minimum and the maximum row sums, as well as the maximum diagonal element. Then we define the quantity that it's, again, a generalization of the row sum. We call it k plus 1 row sum, and it also depends on the power of the matrix. The notation over here means that we take the sum of the ith row of the matrix A raised to the power of k. Using this notation and by taking the kth root of these quantities, we managed to obtain sharper bounds for the spectral radius. And in fact, as k goes to infinity, we proved convergence to the spectral radius. As you can see in this graph, the blue line denotes the value of the spectral radius, and these are the upper and lower bounds, the sequence of upper and lower bounds created by finding these quantities. Then, by using the W quantities and also some expressions of the maximum and the minimum elements of the matrix, we managed to take even sharper bounds with the quantities that were defined Zn and Zl, as you can see over there. Actually, we proved that they are sharper than W, meaning that and also the convergence is even faster. For further information, I'd like you to, I invite you to come and discuss it in the coffee breaks. Thank you.
αντικείμενο έχει το συνέδριό σας?
Right. Where is this PC?
Check files if they work appropriately.
Oh, NASCA, there it is. Right, and what I want to do is minimize the, can I go copy? Right, no, oh gosh, I want to close this, I want to copy it. Copy? How do I copy this? Copy. Control. Which machine is this? It's an HP. Minimize and then stick. And then, oh, there it is.
I put it in front of you.
Okay, and if I open it, should I open it now?
Yes.
And we want to maximize, we want to get rid of this.
View.
View. View full screen, I think it is.
Yes.
Oh gosh. Is it here? No, it's. What about that?
Oh, yes.
If you can find the where the thing is. I had this. Go there. Hallelujah. There is life after.
We check the file.
You know, this there is life after death.
Oops,
sorry.
No, it's okay.
But you have another one.
Yes.
But no more than one more.
Yes.
Αγγελική, να βάλεις και σε μένα το στικάκι.
Ναι, τώρα να βγάλω το δικό μου. Close current. Να βγάλω και το στικάκι. Για βάλτε το δικό σας. Για πείτε μου, πού πάμε.
Λοιπόν, θα κάτσε, πάμε, έχει NASCA 23. Ωραία, το ανοίγεις και έχει μέσα, εδώ πήγαινε πιο κάτω, κάπου πρέπει να έχει Littoral, NASCA 23 Finance, PDF.
Είναι με τα ονόματα, δεν είστε πιο πάνω.
Ναι, ναι, στο ένα.
Όχι, δεν έχει. Μήπως το έχει γράψει ελληνικά. Μήπως είναι στο Littoral.
Α, ναι, για πάτα, στο Littoral. Να, το αυτό.
Εμένα καμιά φορά ξεχνά τις λέξεις. Περίεργος πώς είναι.
Curious.
Curiosity.
Curious.
Ξεχνά τις λέξεις. Δεν δουλεύει, εντάξει είναι.
Ναι.
Πότε θα βάλει και ο Τζον μετά.
Ωραία, οπότε μάζεψε τα μαζί.
Από πάνω έχει το δικό.
5 και 5 θα αρχίσουμε, έτσι. Έχουμε ώρα.
Ωραία. Ναι, ναι, ναι. Και το Τζο είναι.
Το έχω ανοιχτό.
Το έχει ανοιχτό. Α, πολύ ωραία. Τέλεια. Μια χαρά. Εξαιρετικά.
Να το βάλω όπως το έχει full
screen.
screen.
Ναι, ναι, βάλτε το. Να είναι έτοιμο.
Να βγάλω το δικό σας.
Ωραία, κάτσε να το βάλουμε. Μια στιγμούλα.
Ωραία, το μπορείτε.
Ωραία.
Let's start. I would like to welcome you in this afternoon session entitled Regularization and Statistical Modeling. We have 5 talks in this session. The first speaker is Professor Joab Winkler from the University of Sheffield, UK. Joab is well known for his significant contribution to various topics in numerical mathematics and computational statistics. Today, he is going to talk on numerical properties of sparse solutions of linear algebraic equations.
Right. Well, thank you. Can you hear me? Yes, that's okay. Well, thanks very much indeed. This is work with my postdoc, Mayo Lakshmi, and this work was motivated by the fact that when we were looking at the literature, we found a huge number of results, but we didn't actually find any verification of the work. How did you know that the results were good, bad, or indifferent? So what we wanted to do was try and put some sort of flesh on the bones. So I'm going to talk about, first of all, sparsity. Then I'm going to compare the least squares solutions and the Lassus problems. And then we talk about cross-validation, the L curve, and I'm going to give you some examples to show that it's actually, not all underdetermined equations have a sparse solution, okay, which you wouldn't think from the literature. So let's continue. Oops. Right, okay. We're only concerned with underdetermined problems. So we have basically, this arises when you have a large number of what are called predictors or feature variables, and you have relatively few experiments. So those occur, for example, in chemometrics, brain imaging, genomics, gene selection, text analysis. So what you really want to do is to select the most important predictors or features. And the motivation for that is if you've got a system that has a large number of inputs and you want to represent it, you say, well, actually, I'm not very interested in inputs that have marginal effect on the output. You want to find the inputs or the predictors that are the dominant effect. So you want to find the most important inputs or predictors that affect the output. So the questions you have to ask is, if you have an infinite number of solutions because you have an underdetermined equation, which model from this infinite set of models should be chosen? What is the criterion that should be used? And most importantly, how can the fidelity of the results from the analysis of data that are corrupted by high levels of noise be guaranteed? So invariably, your data are corrupted by noise. So simply producing a solution and not verifying it is of little use. So what we attack this problem by solving this constraint minimization problem. And it looks very similar to ridge regression or Tikhonov regularization, but it differs in one way. You notice that there's a one norm constraint rather than the square of the two norm, and that has 2 implications. First of all, the one norm is not a differentiable norm, so there's very little you can do to progress from that. And secondly, there's no one norm matrix decomposition, so there's nothing equivalent to the 2 norm that to the SVD for the 2 norm. It just doesn't exist. You can okay, you can see as lambda tends to infinity and you minimize that, you can say, well, the first term will become irrelevant and you're just going to get the 0 solutions. If lambda is so large, all you're going to get is minimize the norm of x1 and x is 0. It's not a very interesting solution. Now, a closed form solution does not exist unless the columns of A are orthonormal, but that's a pretty restrictive case. But nonetheless, you can get some fairly useful results just by some fairly simple analysis, okay? So what do we want to look at? Does every underdetermined least squares problem admit a sparse solution such that the Lassus solution is an exact solution? So if you have an underdetermined problem, you've got the least square solution in the null space. Can you add a vector from the null space such that the least square solution and your vector from the null space is a sparse solution that satisfies your data exactly. And does there exist a condition such that it can be determined a priori if a least square solution has a sparse solution? I don't really want to do the entire computation, say, oops, it doesn't have a sparse solution. Can I actually work it out if it has one before I actually do the computation? And then I want to know what's the geometry of the difference between the least square solution and the Lassus solution. Okay, now, okay, so let's try to work out some very simple properties without actually solving the problem, just by looking at the problem statement and saying, what can we deduce? I'm only looking for the underdetermined problem. So I've written my SVD, as you can see. So it's my sigma is a diagonal matrix. Right, okay. And I've written the V, I've decomposed my V into V1 and V2, where the columns of V1 form an orthonormal basis for the row space of A, and the columns of V2 form an orthonormal basis for the null space of A. Now, assume that I can solve my Lassus problem. So there is a solution that is some function of my weight lambda. I don't know what it is, but I'm just going to assume abracadabra, I found it. Never mind how, and it satisfies my data exactly, because that's what I'm after. I actually want a solution that will represent my system. So it's got to satisfy my fundamental equation. And I also have my least square solution, XLS, and I can add to it any vector in the null space. So since columns of V2 form an orthonormal basis for the null space, V2 times D1 is any vector in the null space. So I've got two equations there, my Lassus solution and my least squares. D1 is an arbitrary vector. V2 forms the orthonormal basis. So all I'm going to do now is just subtract these two equations, and I get the equation at the bottom, okay? And I say that's a homogeneous equation, and then, so when I solve that, I end up with, you see, oops, sorry, wrong one. This bit here, A times something is equal to 0, so that something is here, and V2 times D2 of lambda is my vector in the null space of A, okay? D2 forms an orthonormal basis for the null space, so any solution would be written like that, and then I do some simple maths. I just take these terms on the left over to the right, and I find that my Lassus solution can simply be written as a least square solution plus some vector in the null space of A, which I can then... So a method for the solution of the Lassus performs computations on the null space in A in order to return a sparse solution. So, and I've written, and just it's very easy to work out those two equations in red, okay? Okay, so V is the right singular matrix from the SVD of A. Okay, D of lambda is an arbitrary vector because they come from the fact that I'm dealing with any vector that lies in the null space. So the question is, what are the properties of A and B such that there exists a regularization parameter that satisfies this solution? Okay. Okay. So it's what I want, let's write. I'm going to write my Lassus of lambda, V times that, V times a vector T. So T is my vector, sigma to the minus 1, U transpose B times D of lambda. And what I want to do, I want to consider the number as the number of 0 entries in the Lassus increases. So does the Lassus, can I get a solution with 1 0 entry, 2 0 entries, 3? So suppose I just want a solution with 1 0 entry, then can I find if VI is the VI transpose is the ith row of V, can I find an index I such that VI transpose times my vector T is equal to 0? If there is, then I can find a value of lambda that will give me one sparse 1 0 entry. But there could be a different value of I will give me another value of lambda. So I can pick as many as I like. That's pretty straightforward. Suppose I want 2 zeros, then I have to solve the equation at the bottom. And that's going to be a bit tougher because here I'm having to solve 2 homogeneous equations, not just 1. So it's going to be, my lambda's got to satisfy 2 homogeneous equations, okay? It can be done, but it's a bit tougher. And I can choose, and I have n choose 2 pairs of such equations. So the first and third may give me value of lambda, or the 8th and 29th, whatever. Not all pairs will, but I can find pairs. Okay. Now I choose k. So I want to choose k equations, so I can do that in n choose k ways. And I say, okay, I've got k equations. This set of k does have a value of lambda. That set of k doesn't. So different sets of k rows yield different values of lambda. And what is pretty clear, I hope, is that as you ask for more and more zeros, it's going to be harder and harder to find them, because you're going to have to satisfy more and more homogeneous equations. They may not have a common solution, lambda, so you're not going to find a sparse solution, okay? So that, and this is something we found in practice. You simply cannot obtain, or it's very difficult to find a sparse solution with a large number of 0 entries. Okay, right. Okay, so the other thing you have to consider is the regularization parameter lambda. Cross-validation is used a lot, but unfortunately it gave us awful results. It's very popular in machine learning. It's used a lot to predict the accuracy of models, but we found it's computationally expensive. And as I'll show in examples, you've got to calculate the minimum of a very shallow function. And I'll show you exact. We used another method that was much better. You're looking for a feature of a curve that is very, very well defined. So the CV, you're looking for a sort of very shallow, a bit like sort of eating soup from a sheet of paper, whilst the other one was really sharp. Okay. Okay, right. So what is this L curve? It's really simple. It's simply from a graph. On the you've got here 2 terms. You've got the 2 norm and the 1 norm. And you think of lambda as providing a balance. You want to find a value of lambda that will minimize the model ax minus b and the constraint, the 1 norm. If lambda is too small, you don't have enough of a constraint. If lambda is too large, you've dropped the model and you've got heavily on the constraint. So lambda is got to form a balancing act. And what's the optimal value that you can, if not minimize, at least make both of them small, okay? And you can determine that from a graph. And this is what you get, okay? So this is pictorially. When lambda is 0, which is at the top left-hand corner, basically the residual is small because your model satisfied exactly, so you can see. But the norm is large, but you're getting the exact solution. But you know nothing about the constraint. As you increase lambda, you go down the left-hand side, so the norm of the solution decreases rapidly, but the residual stays the same, so you're doing well because your constraint is imposed, and there's no penalty on the residual stays constant. And then you hit the corner where I've written lambda equals lambda opt. When you get to lambda there, it goes horizontal, and there you have, the constraint stays the same, but the residual increases. So the value of lambda in the corner is the value that will minimize or make small, won't minimize, both the constraint and the residual are small, and that's what you want. And so what we used was this L curve, and it gave really, really good results. And you find the corner is well defined, okay? So let's have an example. We took a random matrix, 50 by 90, and obviously a vector of, and we added noise, signal to noise ratio 30, and we adjusted, and what we did, the solution, the least square solution was such that 40 components of x, which are of dimension 90, were 10,000 times larger than the other 50 components. So 40 components were 10,000 times larger. So if you're going to minimize the 1 norm, you would certainly expect that the 1 norm to have greatest effect on those components that are 10,000 times larger than all the other, right? Okay. The solution, that's the solution of the lasso using tenfold cross-validation, and it gave me 25 zero components, all wrong. Both, you can see I've got the solutions with noise and without noise. The solution is really bad. I should have had 40 zero components. MATLAB uses the mean square error from cross-validation, and what you're looking for is a minimum of a function. You can see it's just awful. You see, how you calculate lambda, say MATLAB returned the minimum and the minimum value of lambda and the minimum within one standard error. Those are what MATLAB returned. So the top graph is without noise, bottom graph with noise, but the point is that not only are the two values of lambda dramatically different, but you can't, it's very difficult to calculate that minimum, or those minima, they're so shallow, okay? But when we used the L curve, you can see that the L curve, both with and without noise, returned 40 zero components exactly, and the tenfold CV, without noise, returned 25 zero components, and with noise returned 85. So the L curve got the exact number of correct zero components with and without noise. The tenfold cross-validation gave us awful answers. Okay, so the solution of the SUL using tenfold cross-validation is sensitive to noise. The minimum is very difficult to compute because it's shallow. And the errors in the 10, if cross-validation, say, instead of giving 40, gave me 39 or 38 or something, fine, could accept that. But it went from, what was it, about 10 up to 85, so it was really bad. The L curve gave me the correct answer, both with and without noise. Okay, now let's try another example. And we looked at, so this is the graph of the number of zero entries. Again, we looked at, I think we looked for 40 zero entries. So 10,000 entries of X were, no, 40, what was it? 40 entries of X were 10,000 times larger than the others, and both cross-validation and L-curve couldn't get the answer at all. So with tenfold cross-validation, the optimal value of lambda was off to, gave me some incredibly large number. With L-curve, it gave me 0. So something's going badly wrong here, because I've got two methods and they're giving me wildly different answers. So what's gone wrong? This is the same type of matrix. It's a random matrix. I just used a different seed for the random number generator, and I used a different right-hand side, but fundamentally, it's the same problem. So what's gone wrong? There's a graph of the mean square error, and you can see that, look at the lambdas, you see, you can't work out an optimal value of lambda. There is no minimum. You can see the means over a range of 8 orders of magnitude, the mean square error is constant, so it's not going to work. Totally bad. Okay. So why did the first example give me really good results and the second one really bad? The reason is that in the first, the least squares problem was ill-conditioned. In the second example, it was well-conditioned. And what we found repeatedly, a sparse solution exists if the least squares problem is ill-conditioned and you only got a few zero entries. Right. If you're looking for too many zero entries, you simply won't be able to compute it. So there's an incompatibility of sparsity and stability. If you want a sparse solution, your least squares problem has got to be unstable. And we found that repeatedly. And then we looked in the literature, and it's been found also in feature selection and neuroimaging. People were building up signals from brain imaging, and they found that there's a fundamental incompatibility. If your least squares problem is well conditioned, you cannot get a sparse solution. Now let's take another problem. You see, these are the two L curves. Beautiful. You see, with and without noise, I get a L curve sharply defined. The way you calculate it, MATLAB's got a toolbox, and you calculate the corner. I did it using cubic splines, okay? And you can see it works really well. The corners, and it returned I asked for 20 zero entries, and you see the red dots with and without noise gave me the 20 zero entries. The 10-fold CV gave me, I think it's 19 zero entries without noise, and with noise it gave me 120 odd zero entries. So not very good. Okay? Now let's just, so least squares problem is ill-conditioned, we've got excellent answers. What happens if you try, look at the L curve with the well-conditioned problem? That's what you get. The point here is that as you start at lambda 0 at the top left corner and you walk down to the right and then drop, it is clear there's no value of lambda that'll minimize both. You're starting off with a large value of constraint, a large constraint, relatively small residual. As you increase lambda, the constraint decreases slightly, the residual increases, and then the constraint decreases rapidly and the residual increases. There is no value of lambda that'll balance both. And this is the L curve you get with a well-conditioned problem. This is typical result. This was said, you simply cannot get an optimal sparse solution with a well-conditioned problem. Okay, so the least squares problem is well-conditioned. The curves do not assume the form of an L, and a sparse solution that does not exist. Okay, and there's the right. So what's the summary? Not all equations admit a sparse solution. Cross-validation we found did not give good results. The L curve gave very good results, even for ill-conditioned problems with pretty high noise level, and an underdetermined problem has a good sparse solution if it has few zero entries and the least square solution is ill-conditioned. Thank you.
Thank you very much, Joe, for a very interesting talk. Comments or questions?
Excellent. Good. Just what
I... Value of some exams.
Yes.
Example 5, the value. Does this value affect your exam?
Yeah, basically.
What is the expected value?
If you make, yeah, 30 will definitely, if the signal to noise ratio decreases, there are one or two complications. You can still work it out, but it's the L, that curve, that corner, it's still there, but it's not as distinct, but it's certainly much, much better than cross-validation. It's much, much better. Okay. Thank you.
Thank you for your nice. Ocean.
Okay, the next speaker is Professor Marilena Mitrouli from the National and Kapodistrian University of Athens. Marilena is well known for her significant contribution to various topics of numerical analysis, numerical linear algebra, computational statistics, including penalized least squares problems. Marilena today is going to talk on regularization and variable selection in statistical modeling.
Is it okay? The screen is full. Is it okay? Yes, can you please show me?
What you have to do?
Okay, perfect. Thank you. So, as working in numerical linear algebra, the last years I have found it very interesting to make a comparison in techniques between numerical linear algebra and statistics. And many times we can apply techniques from numerical linear algebra to improve statistical techniques and especially to study statistical modeling. So, in my talk here, as Joab mentioned just before, again we study the applications when we need to study the prediction of the output of a physical system, exactly the applications that Joab mentioned, which leads to the mathematical formulation that I have in the bottom in a system which of course is not square generally. It has m rows, n columns, and again the right-hand side vector b. So we cannot solve it directly as a linear system, since it is not square. We are looking for the solution x, of course. So what we usually do in numerical linear algebra and numerical analysis generally is to move to least square solutions instead of solving a of x equal to b to minimize the norm of the error, standard least squares techniques, and also always suppose that the vector b will be contaminated by error, what we usually do. So we are working with an b with an error added, and as we know, the accurate approximation, if we apply Moore-Penrose techniques, is given by formula 1, is the ordinary least squares estimator, which usually, especially due many of the times of the error that is introduced, it is not so much satisfactory for the solutions that we are getting. So, what we usually do in numerical analysis is replace 1, the equation 1, by applying regularization, and we start speaking here about Tikhonov regularization. Joab, in his lecture before, spoke about L1, about lasso, L1, L-curve. Anyway, Tikhonov regularization is mostly useful because it is also connected, this numerical linear algebra approach that we have, with what in statistics also is used in their model. In statistics, the systems applies us the linear regression model. We have, let's say, a different mathematical formulation of this form, where matrix A that we use in numerical analysis here is matrix X, which is called the design matrix. So it is mostly oriented to the experiments, is the design matrix. Again, non-square of order P times D. Psi now, the so-called B of us as the right-hand side vector now is Psi, the data vector. And what it is of interest here about the noise that just Professor Vrachatis before asked Joab, in statistics, always the noise that is involved is picked up randomly. Usually the error vector, as it is called, is selected by a normal distribution, usually, according to this description. And the vector B, which we want to actually compute, the regression vector, is considered as the minimizer of Tikhonov regularization, which in statistics most of the times appears as rich regression.
So we have the two approaches, in numerical analysis, classical Tikhonov, in statistic-rich regression, and it was really of interest that sometimes in papers that we have submitted, it was posed the question, is rich regression the same with Tikhonov? That's why we find of interest to study this collaboration between these two fields. So, anyway, when we involve regularization, either Tikhonov, either one that Joab mentioned, either Lasso, the main task is that we involve the regularization parameter or the tuning parameter lambda, as it appears in statistics, which is not an easy task. How are we going to compute and what values are we going to give to this lambda? So one of the approaches, except generalized GCV, is the generalized cross-validation function. Joab mentioned about the CV, cross-validation. Also exists L1 curve. One of the most popular, which mostly applies in statistics, is the GCV function. And what is the benefit with this GCV function that we have studied a lot also in numerical analysis, is that this function is defined by this quotient, where the matrix A of lambda that appears is called the influence matrix and is given by the expression that is mentioned here, alpha lambda. Lambda is the tuning parameter, and due to this very important paper of Graven and Waba in 1971, made, let's say, a useful path that you can select the parameter lambda as the minimizer of this function. This is a very popular approach, that the minimization of the GCV over lambda gives us a good value, a good approximation for the tuning parameter. Many scientists, many researchers have worked on this topic, how this minimization is the better way to be applied, because as you can see, the quotient of this GCV is not a simple one. It contains a complicated numerator and denominator. So, what was really important is a work proposed by Lothar Rodriguez and his collaborators in 2009, into which, by using a classical matrix identity, which is mentioned here as identity, they replace the classical GCV definition with another equivalent quotient, V of lambda, which has as numerator a bilinear form, and as denominator the trace of this matrix vita, which is just defined in the line above. So, in order to avoid the direct computation of GCV, which is expensive, it is definitely cubed, we move to minimize this bilinear form, this quotient, with a bilinear form as numerator and a trace as denominator. And now it is really important that this quotient can lead to an estimation of the GCV. Not direct computation, which will be of cubed complexity, but it is important here to see that instead of the direct computation, to estimate this quotient, because especially the numerator, as a quadratic form, can have nice quantities and nice formulas for deriving estimates for this. So, there is much work in the literature, and many approaches have been developed by many participants of NASCA conference too. I can mention Lothar Rachel, Alessandro Buccini, Caterina Fenu, Rodriguez, their teams, that they have a lot worked on this, Youssef Saad also for GCV function, and many approaches have been developed, other based on Gaussian quadrature techniques, other based on extrapolation techniques, other for other formulas. And what we are recently studying, and we find it interesting, is a heuristic approach. If we can develop a heuristic approach for approximating the quadratic forms, which can be rather simple and effective in practice. So, how we can define the heuristic approach, especially if we have a symmetric positive definite matrix, and our task is to estimate such a quadratic form of the general form x transpose a to minus m for a physical m x. This is the quadratic form. So what we mean as heuristic approach? As heuristic approach is by defining an appropriate index, which we named it as generalized index of proximity, which actually is given by the quotient of relation 2. We can see that actually contains some inner products, actually. By the following lemma, we see that is easily computed formula always take values larger or equal to 1 and is equal to 1 if and only if x happens to be eigenvector of matrix A. This proof can be easily done, and the proof uses actually the Cauchy-Schwarz inequality, and from this we can see the following. Since this index is exactly 1 if x happens to be eigenvector, what about if this quotient is around 1? Not exactly 1, but around 1. Then we can have this equality, which is mentioned just after the proof of this, an equality which actually expresses and uses two parameters, n1 and n2, and by expressing this equality, which actually is true if he is any eigenvector, but it will be approximately true if x, this index of proximity, is around 1, what we achieve from here is by performing all the intermediate operations, we can finally have an estimate of this inner product, which actually is the quadratic form. So the inner product x, a to minus m x, can be estimated by this formula, which is a multi-parameter formula, contains two, as we can see, two integer values, and actually we have a family of estimates for this quadratic form. The computational complexity of this formula is very simple because it contains only MVPs, and actually it will be of square complexity. The question here is how it performs in real data. If we use this heuristic estimate, is it satisfactory when we test it in real data? So let us see to this quotient of the GCV to apply heuristic estimates. And what to do is to test real data. The notion of correlated data appears very frequently in statistics, and usually in numerical analysis we don't study so much correlated data. We use random data, but we don't pay attention to this property, which in real data is very important. When we have the design matrix, as it is called in statistics, all of its columns, which in statistical literature are named also covariates, all of them appears to be correlated. They are correlated between each other, and if we think it as a physical system, correlation is a very natural property because all influence each other. They are not completely independent, the columns. So the definition of correlation is, in a statistical experiment, to choose the covariates, the columns, for example, from a normal distribution with these characteristics, and the correlation is defined according to this nice relation, the correlation Rij between two columns, two covariates of the matrix, is defined by this quotient. Actually, you can see that numerator is the inner product of these two columns, Hi transpose by Hij, and the numerator is the norms of the columns. The denominator is the norms of the columns. And the correlation can be from -1 to 1. So this is a real property that the data can be characterized, and what we did is perform a simulation study with correlation data and test these heuristic estimates. What was really of interest is the following. We simulated many data sets according to these characteristics, the standard linear regression models. We picked up the columns of the design matrix, the covariates, jointly distributed from a normal distribution. We tested, in this example that I will present, high correlation. You see the correlation structure is 0.999, so we have chosen very highly correlated data, and we shall check the speed-up factor if we compute, if we solve, we find the regression parameter beta of this model by performing the exact GCV computation according to the mathematical formula over the heuristic estimate GCV according to the heuristic formulas that we have attained. And we will also try and check the mean square error that appears here. So in this example, which, as we can see, this example is an overdetermined case, more rows than columns. We can see here in this matrix the following, in this table, the following interesting information that appeared. We can see in the first column the variance. Let us check the mostly appearing value of variance in statistics, which is 1. The method that we have tested, exact GCV, for the solution of the regression problem, and 2 heuristic estimates, because as I have shown, we have a family of heuristic estimates. And this is important because we can pick up the values of the parameters. Also, the value of lambda that have been computed, the required time, the speed-up factor, and the mean square error. What was really impressive is that, as you can see, the heuristic estimates behaved very well. We have reduction to the time instead of -2 to -3. The speed-up factor between the 2 heuristic estimates versus the exact GCV is really important. The mean square error that appears, we see here 10 to -1, which for numerical analysis cannot be satisfactory, but for statistics is enough. Because in all statistic applications, they don't care so much about large, let's say, error and large accuracy. An accuracy of -1 or -2 is okay for them. And what was really important is that mostly in all these random cases, the index of proximity that the data have shown was around 1. So the data show that they want to be treated heuristically. And when we tested the probability of this index of proximity to be less than 1.1, at least of almost 74% cases, this index was less than 1 in random cases. So, by tested 10,000 of them, we saw that the index of proximity to be larger than 1, smaller than 1, was satisfied in so many, in 7,000 cases almost. So this was an important information for our concluding remarks about the following facts, that if we use this heuristic approach, and on Wednesday another collaborator of mine will develop in extended way how we can have families of heuristic estimates which can also be applied N for L1 curve, N for L curve, and as we can see can be very easily reached. The estimate GCV function achieve regression estimates with much better results than the exact order. Also, for highly correlated design matrices, but and for other matrices too, that the next speaker will show in his experiments, we see that the estimated GCV can be recommended for applications. Also, according to the timing and the speed-up factors, we have seen that the heuristic estimates were very fast. And finally, and what is the interesting problem that really I am very, let's say, enthusiastic about it, is that the trend of our period now is test the data and learn from data. So data leads to treat them heuristically. And we study more on this case because we can see that the data can lead us to a nice heuristical approach. And also, what is now under consideration is, again, when we say learning from data is that maybe regularization, that as we have seen, okay, we say in post-regularization is a difficult task. How are you going to perform it? How you will choose the parameter is not so simple. And again, we can see that from the data, regularization sometimes may not be needed for high-dimensional data. From a study that we have started again in statistical models, high-dimensional statistics is when we have many columns and less rows. Big data is if we have many rows and less columns. In high-dimensional, and this is topic under research now, maybe regularization can be avoided and don't have all these problems how to estimate lambda. But in any case, I think that it's really very important by the testing and the performance of the data to conclude and have interesting results of the way that they can be treated. And this is the end of my talk. And thank you very much.
Are there any comments or questions, please? Yes, Professor.
Thank you for your very nice lecture. Yeah, I'd like to ask you, instead of using the noise strength, to use a vector of standard. One noise strength, so yes, yes, wait.
Different entamo. Please. How we can prove it theoretically?
Thank you again, Maria. The next speaker is Nikolaos Koukoudakis from National Capodistria University of Athens. His talk is very interesting. Koukoudakis is going to speak on learning from data, how to treat correlated data set.
Hello, good evening, ladies and gentlemen. Today we will talk about learning from the data, how to treat correlated data sets. I am a third-year student at the mathematics department of Athens. And our main problem today is the least square problem, y equals x vita plus epsilon, where x is the design matrix. Now, the design matrix has n rows, d plus 1 columns, and we want to find the regression parameter, vita. We will add a small noise epsilon, and that is to check the system stability regarding X's structure. Now, to solve this problem, we have two possible paths. First one is the direct method, MNS, minimum norm solution. We will have to minimize this norm, which looks pretty straightforward. However, our second path is the regularization techniques. We can use either Tikhonov regularization or LP-LQ regularization, but now we have to be careful. These methods require us to solve a wholly different problem, as they feature new parameters. Solving that kind of problem requires many algorithms to be implemented to find the ideal value of the parameters, and that can cost us a lot of time, which is of course valuable. The objective of our research is to study the data matrix X and its properties, and to decide and answer this very important question: is regularization really needed or not? Now let's head on to the first method, the minimum norm solution. This kind of method looks really simple, and we can minimize this norm through various ways. Now, after a lot of mathematical operations and work, we have come up with a formula that is shown on the screen. Now, we note that this kind of matrix is called the pseudo-inverse matrix of X, and it is very useful when a matrix cannot be inverted. The second formula is equivalent to the first and can also found the minimum norm solution, but here we apply the SVD, which is a type of decomposition for matrices. Now, for the second way of our second technique, we apply regularization. This is the Tikhonov one, or also known as ridge regression. We try to find the optimal value of lambda. There are many ways to do that, but we use Brent's algorithm, which is also used by Julia's package regularization tools. Now would be a good time to say that we have applied Julia's algorithm, and our whole algorithms are implemented in Julia. These two formulas represent the solution of the Tikhonov case for a given lambda. So if we have a given lambda, we can find how the regression parameter is computed, and we can later find the relative error to see how close we are. The third and final method is the LP-LQ regularization. Now here we have not one, not two, but three parameters, which makes things really difficult to find the optimal values of the parameters. We need to be really careful, and in order to use this method, we have to be sure we really need it. Now let's see our data sets. The first way of constructing the design matrix is what we call the CCC, which is the column correlated covariates. In this method, we use a diagonal covariate matrix, and we use this matrix to compute the columns of X. The correlation coefficient can be computed between these two columns in the way as we see it on the screen. Now, the second method of creating a dataset of creating a data matrix, as we call him, is the ECC, the element correlated covariates. In this method, we use this sigma matrix, which is, of course, square, and we use this property as we can see. A general example of the structure of sigma is shown, and we can see, of course, that the diagonal values are all 1, so the covariation sigma is exactly 1. Now let's see the algorithm. The construction for the ECC model is as shown, and it represents all the aforementioned properties. Now our third way of construction, the design matrix, is the toy model. Now the toy model is a very simplistic model which uses a lot the normal distribution for y and ui, and so we can have each column to be correlated with another one for x's columns. This may be very simplistic, although one could say it's not so realistic, but that is not why we're here. However, if one seeks a really realistic model, that's the next one. This is the spiked covariance model. This applies to real-world problems, and what does that mean? It means that the sigma matrix, the covariance matrix, has eigenvalues that are both above and below 1. Now let's see an example. On the right part of our screen, we can see for n equals 3 and r equals 0.25 that we have this matrix, and if we compute the eigenvalues, the lambda 2 and lambda 3 are indeed below 1, and lambda 1 comes as a spike above 1. And that really verifies this property. So for this method, we compute the X matrix through the normal distribution with mean 0 and covariate matrix sigma. Now let's see the numerical implementation. How are we going to compare those methods? We're going to compare them using the relative mean square error. What does that mean? We take the mean value of the relative error, and it is squared, as you can see. Let's see our simulation scheme. Let's analyze it. We have a given data matrix, X. Now we generate a random regression parameter, beta, which is, of course, generated by the normal distribution. Then we create 100 training sets, and we put noise in the y. Now, as you can see, epsilon has an index I. That means that every time, in every training set, epsilon is different, the noise is different. So we can have a more generalized conclusion. At last, we compute 3 vectors, 3 approximated regression parameters in order to calculate the exact one. Let's see the results. They are very complicated, and we will see the general conclusions for each data set. Now we can see that for minimal R, you can see that we have R 0.5, 0.9. The MNS seems to be not having any severe trouble locating and finding the exact vita. However, when R equals 0.999, it's having serious trouble. Now, this is what we need, that this is what we call regularization needed datasets, because this error is too large and cannot be tolerated. We can see that the premise is verified in the later datasets by having a greater matrix. Now let's head on to the next dataset, ECC. We remind that it's element correlated covariates, and we can see that it is also verified as well. We try to generalize with bigger and greater values for the dimensions of X, and we see that our premise is confirmed. Now let's head on to the toy model. For the toy model, we can see that the MNS is also very inaccurate for 0.999, and regularization is mandatory in these parts. However, we can also see that this is an overdetermined case. What does that mean? That n is greater than d. However, as we experiment and increase d, we can observe some changes. Now d is 50, 75, and now 150, and then 1000. What does that mean? We can see that MNS is incapable of finding the accurate regression parameter. However, for d equals 1000, the MNS is satisfactory. We believe that that can be generalized, so we tried in the spiked model, which is more realistic, and we see that it is indeed confirmed. Lastly, our conclusions sum up that regularization is needed only if X is highly correlated. Now, highly correlated, as we saw, is when R equals 0.999, and with R equals 0.9 or below, that MNS offers satisfactory results. Now, if MNS produces satisfactory results, that means that we can avoid regularization, and now we can save time, which is very valuable. However, some additional conclusions are that when D increases, which means that the matrix is high-dimensional, regularization can offer little or no improvement at all. And that is very interesting because we can avoid regularization in this case too. However, one last conclusion is that we tried implementing the Tikhonov regularization for and experiment with lambda. Now, if we try lambda below the optimal lambda, which we call lambda best, we see different paths. Now, in the first path, when D is really big, which means we have a high-dimensional problem, we see that that all lambdas below lambda best give very similar regression parameters and approximate the solution really good. However, as D gets smaller and we have equivalent n and d, or d is less than n, so we have an overdetermined problem, lambda best is clearly the better solution because the other lambda below lambda best offer very inaccurate solutions. With these conclusions, we can see that in this way of exploring and researching with the axis properties, we can learn from the data, and we can save time as we explore linear algebra properties. Now, with this scheme, we can sum up what we have already observed and mentioned, and now, with a few rules, we can avoid very important tasks that some consider to be mandatory. Thank you for your time. If you have any questions, please feel free.
Are there any comments or questions? I have a short question. How you select the values of P and Q in LK?
Thank you for your question. Let's head over to the respective slide. Now, P and Q are very hard to find. And there are many complicated algorithms. However, we use we find arbitrarily the values of P and Q, and we often use brute force algorithms, which are yet slow but fully effective.
Are there any other questions? Yes, Professor.
Convex norms applied.
Excuse me, could you repeat, please?
When a norm is called convex norm. Convex. Also, you can apply for non-convex norm. I think if you like, you can go to test it.
When P is more than 1? Smaller, oh, okay. Yes, we have tried many values of P and Q, and we haven't seen the real impact that the P and Q have when they are smaller than 1, which means that the best solutions they have to give is when they are closer to 2.
Operative study of some variable selection method for generalized linear models.
Hello, everyone. We're going to talk about some variable selection methods for generalized linear models, and especially for a linear regression model. First, we're going to talk about supersaturated designs and the linear regression model. Then we're going to talk about the method called sur-impedance screening, or SIS, as we are going to say it later. An important part of statistical process control, cumulative sum control charts. Our proposed method, SIS-CUSUM, with some experimental results. We're going to perform an example, and then we're going to say some concluding remarks. Supersaturated designs, or SSDs, appeal greatly to both scientists and engineers. They are designs with P factors and N runs, where N is less than P. They first appeared by Satterthwaite in 1959, and there is a comprehensive review about the analysis and the construction of SSDs proposed by Year. Their assumption, their analysis relies on the assumption of F sparsity, where only a few factors are significant. The main aim of a screening experiment is to correctly identify the active factors. The inactive ones will be discarded, while the active ones will further investigate in the following experiments. During screening designs, we consider the null hypothesis and the alternative hypothesis, where you can see that we have active effects. Our proposed method, cis-COSUM, that we're going to say like this, detects the active factor via the COSUM chart in SSDs, assuming that we have a normal distributed response. There are two stages. In the first stage, we apply a raw screening procedure using Sur-independent screening, and then we detect the active factors via the COSUM chart. During our proposed method, we evaluate its performance using some criteria. First, we compute type 1 error, which is the cost of declaring an active factor to be active. I.e., we reject the null hypothesis where it is true. Thus, a type 1 error results in non-significant active factor being identified as important. Then we calculate type 2 error, which is the cost of declaring an active factor to be inactive. Both of them must be kept as low as possible. Furthermore, in SSDs, it's very good to control and keep as high as possible statistical power, which is more critical than controlling type 1 error. Let's consider the linear regression model that is given by equation 1, where y is the response vector, x is the design matrix, beta is the vector of unknown coefficients, and epsilon is the random error vector. Our goal in factor screening is to identify the non-factor effects, assuming that there are only M to M active factors from the total P involved. Sur-independent screening, or CIS, it was proposed by Fan and Liv in 2008, and it extracts the active factors assuming this property of sur-screening. It is a variable screening procedure which selects the important effects with probability tending to 1. It screens out the important factor with a component-wise regression after a regularization, so its predictor has 0 mean and standard deviation equal to 1. Let M star be a sparse model with non-sparsity size S. The remaining P minus S variables can be correlated via the response variable via the linkage to model effects. So let W be formed by component-wise regression, where X is the standardized model matrix and Y is the response vector. Then W is a vector of marginal correlations of the predictors against the response variable. We consider gamma, with then the P factors components are sorted in descending order, forming the M gamma submodel. This is a way to minimize the prime model to the submodel with size D, which is less than N. The computation complexity of this method is O of NP, while it's invariable at the scaling, since it's using only the order of component-wise magnitude of W. Therefore, the use of CIS is identical to selected predictors using the correlation with the response. Now let's talk about a COSUM chart, which is an important chart in statistical process control. It's proposed by Page and is used in statistical process control in order to identify shifts and of magnitude small or medium. So let xi be an individual observation in the process. When the process is in control, xi follows normal distribution with mean m0, which is the target value of the process, and sigma, which is the standard deviation, which is known or in multiple cases needs to be estimated. The upper and lower COSUM statistics are given by equations 2 and 3, where C0 plus and Z0 minus are the starting values, and K is the reference value. If either Ci plus or Ci minus is greater than h, which is the decision interval, then the process is out of control and Kusum will signal a change. Note that both reference value and the decision interval depend from h and k lowercase. So through simulations and according to Montgomery, we have to find the best values of h and k in order to provide a Kusum with good performance. Now, we used this method from before and Kusum in order to propose our procedure. This Kusum procedure is described as follows. Let X be an SSD matrix, where Xi is the ith column of the matrix, and Y is a normally distributed vector of responses. We compute the least squares estimator selecting beta j using this technique, and this can be done since M, which is the active factor, the active effects, is smaller than the half of the runs according to the effect of the effect sparsity assumption. We calculate the absolute values of the estimates. We set the standard deviation of the effects equal to the square root of the standard error of the linear regression model. And this, again, can be done since the M value is less than N. We choose, according to Montgomery, K and H so to acquire Kusum with good performance, and then we calculate the decision interval and the reference value of the chart. We calculate only the upper statistic with the absolute estimates as the inputs, and we set the mean equal to 0 as the target value and the starting value different from 0. If Ci plus is greater than h, then the ith effect of the model and all the effects with larger magnitude diverge from the target value, and we can say that this is the active ones. If none of Ci plus are greater than n, then none of the effects deviate from 0 mean target value, and then we can say that none of the active effects, there are no active effects in our experiment. Note that we only computed the absolute estimates, so it is a good idea to compute only the upper statistic of the chart since the lower statistic is always 0. The estimate of inactive effects are supposed to have 0 mean, and according to our simulations, setting a starting value different from 0 has better results than giving the starting value a 0 value. We perform a simulation sim where we conducted various simulations using different sizes of NP using SSDs proposed by Kokovinos et al., Marilyn Woods, and Tang and Wu. We compared our method with SIS itself, standard stepwise variable selection procedure, and dancing selector or DS by Fo et al. We performed 1,000 simulations we performed for each model, where the response variable were generating according to the linear regression model for each experiment. An SSD was considered as a design matrix, and the epsilon is identically and independently distributed following normal distribution with 0 mean and unit variance. The number of active factors of the model ranging from 1 to the half of the runs, and beta coefficients were generated from normal distribution with mean me and unit variance corresponding to the active factors, while the values corresponding to the inactive factors were set equal to 0. Active factors were selected using our method and DS and stepwise. Kusum parameters were selected according to our simulations K 1.5 and H 1.61, and a heuristic approach was performed to select C0+. Type 1 and type 2 errors along with statistical power were calculated. As far as for the C0+ starting value, according to our simulations and according to the type error values, we saw that C0+, which is the starting value of the chart, can be calculated using equation 4. We can see that this equation depends on the number of runs, the number of the active factors, and the number of the predictors. For example, if N is 12, P is 22, and M is we have 3 active factors, then the C0+ is 15. According to our simulations, SIS Kusum improves the performance of SIS. It keeps type 2 error values as low as those of SIS. it reduces type error up to 20%. Comparing cis-QSUM with stepwise and DS shows that cis-QSUM produces low type 1 and type 2 errors, especially for active effects up to one-third of the runs. The mean of the type 2 error values of cis-QSUM, taking into account all the considered models, is lower than 10%, while the mean of type 1 ranges from 40 to 41. Type 2 errors are lower than type 1 for up to half of the runs in active factorial effects, and we have better statistical power for all the considered models. Next, we performed an example presented by McGrath et al. It's about the production of immediate release ciprofloxacin in tablets. The design that we see in our slide, it's 12 runs and 11 factors, and we have a multiple response variables, Y1, Y2, Y3, and Y4. According to McGrath et al., they performed two procedures. The one-stage procedure, they selected all terms at the model at once. Note that they used the main effects along with the two-factor interactions. So they used 11 main effects and 55 two-factor interactions. In the two-stage procedure, they selected only the main effects, and in the stage 2, all two-factor interactions that meet the weak or the strong heredity condition are added, and then they selected the final model. Note that strong heredity is if the model includes A, B, it includes A and B factors as well, while weak heredity is if the model includes A, B, at least it includes A or B in the model. McGrath et al. Used in the first one-stage procedure SCAD method along with CI criteria, while in the two-stage procedure they used SCAD-C, ball correlation basis and length, along with SCAD-C in stage 2. In our case, during one-stage procedure, we used cis-QSUM, while in two-stage procedure, we performed cis-QSUM twice. Note that as McGrath et al., we performed our method individual for each response variable. So, for example, during one-stage procedure, SCAD-C identifies F as active one, while our method identifies F and IK as active ones. During two-stage procedure, performing SCAD-C twice, and the length along with SCAD-C identifies D and F as active ones, performing B correlation along with SCAD-C identifies DEF, A, B, BF, and EF as active ones, where our method performing cis-QSUM twice identifies DF and the interaction DF. Similarly, we performed our method and the other methods individually for each one, and we see the other results. So, as we can see, SSD analysis constitutes a challenging area of research. Our method can be used for selecting important factors in SSDs in case of a linear regression model. A two-stage case is used for analyzing SSDs. First, we use cis procedure, and then we use QSUM procedure. We can see that cis QSUM manages to screen out true active effects up to the half of the runs, keeping type 1 and type 2 as low as possible, and the statistical power achieves better results compared to the other methods. A similar procedure can be performed for assuming that the binary distributes the response, while further research in multiple response analysis screening experiments can be done. Some references that we used. I would like to express my thanks and gratitude to the organizing committee of NASCA. Thank you for your attention.
Are there any comments or questions, please? Short question, Angelique. The method can be extended to
Yes.
It's been done?
It has been done. We used the information theoretic measure for the first case for a screening procedure, and then we performed QSUM chart in order to screen the active effects.
Any other question? No? Thank you, Angelique. And the last speaker is Mr. Ioannis Iordanis. graduate student at the National Technical University of Athens. Ioannis worked in interface problems between design of experiments and machine learning. Today, he is going to talk on the efficacy of conditioned and progressive Latin hypercube sampling in supervised machine learning.
Hello everyone, my name is Ioannis Jordanis and I'm going to present a study about improvement of classification accuracy using progressive Latin hypercube sampling in supervised machine learning. This is a study that was prepared by Professor Christos Kokouvinos, Iliana Silou and me. First, the motivation, the key idea and the objectives of the study will be presented. You will be introduced to some definitions and the methodology will be presented with a consolidated description of the respective algorithms used in this case study. Then the main results, and we will close with evaluation of the proposed method and the conclusions. The statistical analysis of trained sets and sampling constitutes a crucial parameter for a machine learning process, aiming at the generation of high-quality datasets for the training. Latin hypercube sampling, LHS, was proposed by several researchers as an effective sampling method. The advantage of LHS is that it provides full coverage of the range of every variable by improving the stratification of marginal distribution. Progressive sampling techniques and progressive Latin hypercube sampling, which is a modified version of LHS, that has been shown to be effective in reducing the computational cost, but maintaining the accuracy. In this study, we propose an approach that integrates PLHS into the classification process, which leads to low computational cost and accurate classification. We demonstrate the effectiveness of this approach on a range of benchmark datasets and compare its performance with random sampling by applying a number of supervised machine learning techniques. Let's see briefly a few definitions. The well-known definition of LHD, where each column is a permutation of integers 1 to m. PLHD is defined as one hypercube that, if split into C predefined parts, each part together with its former ones constitutes a Latin hypercube. The LHD approximation index, which derives from the ratio of the matrix's elements without any repetition per column, over the total number of the elements of the LHD matrix, which is from this formula. In our case study, we applied the following methodology. First, we created the PLHS algorithms and we selected 3 datasets. Each dataset was split into a 70% as train file and 30% as test file. From each train file, we produced 4 different size samples: 15%, 30%, 45%, and 60% of the train file. All samples were created using both RS and PLHS, and we repeated this procedure 6 times in order to get 6 series of different sized samples. Finally, using ML models, we calculated the accuracy indices, we made comparisons and derived conclusions. In order to apply PLHS on datasets with discrete values, we created CPLHS and PLHS-CH algorithms. The purpose is to produce nested samples. That is, each sample to be nested within the next sample. For example, for the production of 3 samples, first we create an LHD sample S1. Then additional records are selected so that together with